The search for answers begins with one of the most puzzling branches of science, quantum mechanics. When the rules of the very small were first uncovered in the early 20th century, they shattered assumptions about how reality operates. In 1905, Albert Einstein demonstrated that light behaves both as a particle and a wave. A few decades later, experiments such as the double-slit test revealed that electrons too can exist in a state of probability, taking multiple paths at once until observed. The very act of measurement seems to determine the outcome. Physicist Richard Feynman once said that nobody truly understands quantum mechanics, yet it forms the foundation of modern technology. Transistors, semiconductors, and medical imaging all rely on principles that defy common sense. But beyond practical applications lies a deeper question. If matter itself does not settle into a definite state until observed, then what role does consciousness play in shaping reality? The double-slit experiment has been repeated countless times with increasingly refined equipment. In one version, single photons are fired toward a barrier with two slits, and detectors record their passage. Without observation, the photons form an interference pattern on the screen beyond, as though each one traveled through both slits simultaneously. But when scientists introduce a measuring device to determine which slit each photon passes through, the interference pattern disappears. The photons behave as particles traveling through one slit or the other. Observation changes the outcome. This is often described as the observer effect. Physicists debate whether consciousness itself collapses the wave function or whether the interaction with measuring devices suffices. Yet the strange parallel remains. In both cases, information is not realized until observed. If observation is so fundamental, it raises another layer of speculation. Could consciousness exist not just within the brain, but as a field interacting with quantum processes? Some researchers argue that brain activity might exploit quantum effects. Conventional neuroscience describes neurons communicating via chemical neurotransmitters and electrical impulses, a process measured in milliseconds. But quantum events unfold on time scales of femtoseconds, a trillionth of a second. That mismatch long convinced skeptics that quantum mechanics plays no role in thought. The brain, warm and wet, seems an unlikely environment for delicate quantum states. However, recent discoveries in biology challenge this assumption. In photosynthesis, plants capture photons of sunlight with extraordinary efficiency. Studies using ultrafast spectroscopy have shown that energy transfer within photosynthetic proteins involves quantum coherence, allowing excitations to explore multiple pathways simultaneously before collapsing into the most efficient route. In birds, navigation may depend on quantum entanglement in molecules sensitive to Earth's magnetic field. These findings suggest that biological systems can, in fact, harness quantum mechanics under natural conditions. If plants and birds exploit quantum effects for survival, it is not unreasonable to ask whether human brains might do the same for cognition. The Orchoir theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum computations within microtubules, structural components of neurons. According to this idea, microtubules maintain quantum states that influence neural firing, producing moments of conscious awareness when quantum wave functions collapse. The theory remains controversial, with many neuroscientists skeptical of whether quantum coherence could survive long enough inside neurons. Yet experimental evidence continues to accumulate that quantum biology is not merely theoretical. The possibility that thought and awareness are rooted in quantum-level processes keeps the debate alive. While physicists investigate the microworld, cosmologists map the largest structures in existence. In 2005, computer simulations of the cosmic web showed filaments of dark matter stretching across billions of light-years, with galaxies clustered like luminous beads along vast, invisible threads. In 2020, astronomers using the Sloan Digital Sky Survey published a three-dimensional map of over 2 million galaxies, tracing cosmic filaments more than 1 billion light-years long. When these images are placed side by side with microscopic scans of brain tissue, the resemblance is striking. Both display networks of nodes connected by filaments. The human brain has about 86 billion neurons forming a network of synapses, while the observable universe contains an estimated 2 trillion galaxies arranged along cosmic filaments. On vastly different scales, both systems form webs of interconnectedness. The similarity could be dismissed as coincidence, an artifact of how networks tend to form in nature, yet it raises intriguing questions. Are there universal principles of structure that govern both brains and the cosmos? Statistical analyses have compared the distribution of galaxies to the distribution of neural connections. One study found that the structure of the cosmic web and the brain share similar levels of complexity and information storage capacity when scaled. This does not imply that the universe is conscious in the same way a human is, but it suggests that information might be a common denominator linking matter at different scales. If information is indeed fundamental, then consciousness might not be confined to neurons at all. Some theories, such as digital physics, propose that reality itself is a form of computation. In 2003, physicist Seth Lloyd estimated that the universe could have performed about 10 to the power of 120 operations since the Big Bang. Black hole physics adds another dimension. According to the holographic principle proposed by Gerard T. Hooft and refined by Leonard Susskind, the information content of a volume of space can be described by the information encoded on its boundary. Applied to the brain, this raises provocative questions. Is consciousness a local phenomenon of electrochemical activity, or could it be an emergent property of information distributed across a wider field? The observer effect returns in this context with renewed significance. If reality at its foundation is probabilistic until measured, then the act of perception gains cosmic weight. Consciousness might not be a passive byproduct of neurons, but an active participant in shaping reality. Physicist John Wheeler proposed the idea of a participatory universe in which observers are essential in bringing the universe into being. Though speculative, such ideas press against the boundaries of science and philosophy. If consciousness participates in reality at the quantum level, then the brain may not be merely processing information, it may be interacting with the fundamental substrate of the universe. Skeptics caution against overextending parallels. The human mind is prone to pattern recognition, finding shapes where none exist. Similarity of structure does not necessarily imply shared function. The cosmic web does not fire signals like neurons, and galaxies do not exchange neurotransmitters, yet science progresses by asking whether coincidences might conceal deeper connections. The resemblance between neural networks and the universe's large-scale structure invites investigation into whether information networks follow universal laws. As neuroscientists continue to probe brain activity with functional MRI and other imaging tools, they uncover complexities that challenge reductionist models. Brain waves, measured as oscillations in the range of 1 to 100 Hz, reflect coordinated patterns of neural activity. Intriguingly, oscillations and resonances are also found throughout the cosmos, from the pulsing of stars to the ripples of spacetime detected by LIGO in 2015 when two black holes merged 1.3 billion light-years away. Resonance seems to be a universal feature, whether in biological tissue or cosmic events. Could consciousness be a resonance phenomenon synchronized with deeper structures of the universe? The evidence remains circumstantial, yet the questions it raises are profound. Consciousness emerges from matter, but matter itself is not passive. It vibrates, oscillates, entangles, and resonates. If the smallest building blocks of reality are uncertain until observed, then the link between observer and observed cannot be dismissed. The mind may not be separate from the universe, but woven into it, just as galaxies are woven into the cosmic web. But if consciousness is part of the universe's architecture, does that mean our thoughts have an impact beyond the skull? Could the act of awareness ripple outward, however faintly, into the quantum field that shapes stars and galaxies? Or is consciousness an emergent illusion, a local byproduct of neural chemistry with no deeper significance? The search for answers demands that we continue looking both inward into the brain's microstructures and outward into the vastness of space. Only then can we begin to understand whether the human mind is an isolated spark or a reflection of the universe itself. The brain's role in this search becomes more complex when we consider its sheer scale of connectivity. Each of its 86 billion neurons forms up to 10,000 synaptic connections, creating a network with an estimated 100 trillion links. Electrical impulses travel along these pathways at speeds of up to 120 meters per second, carrying sensory input, memory, and decision-making signals. Neuroscience has mapped many of these processes, yet the mystery of subjective experience remains. How does electrical activity translate into awareness? This unresolved gap is known as the hard problem of consciousness, first framed clearly in the 1990s by philosopher David Chalmers. The hard problem asks why brain processes feel like something from the inside instead of being purely mechanical. This gap opens the door to exploring whether consciousness draws from deeper physical principles than classical neuroscience alone can explain. Quantum theories of consciousness attempt to address this divide. The ORC-OR model is one attempt, but others look at entanglement as a possible mechanism. Entanglement allows particles to remain correlated even when separated by vast distances. Experiments in 2017 linked photons across 1,200 kilometers using satellites, confirming that entanglement persists at large scales. If particles within the brain can maintain such connections, could thought itself be entangled with the universe? While mainstream science considers this unlikely due to the fragility of quantum states, the possibility cannot be ruled out entirely. Entanglement does not respect classical distance, and in principle, it could allow information in the brain to be linked with information in remote parts of reality. One of the most intriguing comparisons arises from the study of networks across different scales. In 2012, researchers compared the structure of the internet, power grids, and brain networks, finding that certain mathematical properties repeat regardless of size. These include scale-free organization, where some nodes have far more connections than others, and small world architecture, where most nodes can be reached through only a few steps. When cosmologists mapped galaxy distributions, similar properties emerged. Networks spanning billions of light years and networks spanning millimeters inside the skull both obey the same statistical laws. This convergence suggests that information storage and transmission follow universal rules that cut across biology and physics. If these patterns are universal, then perhaps consciousness is not a local phenomenon, but a property that emerges when networks reach a certain threshold of complexity. Some researchers call this integrated information theory. According to this framework, consciousness arises whenever a system integrates information in a way that cannot be reduced to separate parts. The brain clearly qualifies. But what about larger systems, such as ecosystems, planets, or even the universe? Could the cosmos itself integrate information on a scale so vast that it forms a kind of awareness? This speculation echoes ancient philosophical traditions, yet it now emerges from mathematical models in information science. A related idea comes from cosmology itself. The holographic principle, rooted in black hole physics, implies that the universe can be described as information encoded on a surface rather than within volume. If reality is informational at its foundation, then consciousness too might be an informational phenomenon. The brain could be one processor within a universal network, similar to a node in a larger computational system. This does not mean the universe thinks as humans do, but it implies that information and awareness might be inseparable aspects of physical reality. This hypothesis also raises questions about time. Neuroscience has shown that our perception of time differs from physical clocks. Brain processes can stretch or compress time depending on attention and context. Quantum mechanics, meanwhile, challenges the flow of time itself. Equations describing quantum states are time-symmetric, working the same forward and backward. At the cosmic scale, the expansion of the universe suggests time has a beginning, about 13.8 billion years ago, but its ultimate fate remains uncertain. If consciousness is entangled with these processes, then our sense of time might be a local construction layered over deeper, timeless dynamics. Memory provides another entry point into this investigation. Traditionally, memory is explained as changes in synaptic strength, chemical signals that make certain neural neural pathways more likely to fire. Yet some researchers argue that this explanation may be incomplete. Certain studies suggest that memory could involve electromagnetic fields or quantum states persisting beyond chemical storage. If memory is partially field-based, then it might interact with external informational fields as well. This possibility links human cognition to larger frameworks of energy and information that extend beyond the skull. Dark matter further complicates the picture. It accounts for about 85% of the universe's mass, yet it does not interact with light, making it invisible to telescopes. Its presence is inferred from gravitational effects on galaxies. If such an enormous part of the cosmos is hidden, could consciousness also involve hidden layers of matter or energy? While direct evidence for dark matter interacting with the brain is lacking, the unknown nature of both makes the parallel difficult to dismiss entirely. Consciousness is invisible in physical terms, just as dark matter is invisible in cosmic terms. Both manifest through indirect effects rather than direct observation. Another dimension of speculation comes from resonance. The brain produces measurable rhythms such as alpha, beta, delta, and gamma waves, each associated with different cognitive states. These frequencies overlap with natural resonances of Earth, such as the Schumann resonance of about 7.83 Hz, created by lightning discharges in the atmosphere. While direct influence remains debated, the overlap invites questions about whether human brain activity can synchronize with planetary or cosmic frequencies. Resonance is also fundamental in physics. Atoms vibrate at characteristic frequencies, stars oscillate, and even space-time itself produces gravitational waves detectable across billions of light years. If resonance is a universal phenomenon, then consciousness might align with it at multiple scales. Artificial intelligence provides a contrasting perspective. Machines now process vast amounts of data with speed exceeding human capacity. Yet despite advanced algorithms, there is no evidence that AI systems experience subjective awareness. This distinction underscores the mystery of consciousness. Human brains and artificial processors both manipulate information, but only one appears to generate inner experience. If consciousness depends on quantum or informational processes tied to the universe itself, then machines built only on classical computation may never achieve it. The difference could highlight how human awareness is embedded in universal laws beyond mechanical calculation. The question of what happens after death sharpens these speculations. When brain activity ceases, electrochemical signals stop and neurons degrade. The energy used by the brain dissipates into heat, but information is not the same as energy. In physics, the conservation of information is a debated principle, especially in the context of black holes. Some theories hold that information is never destroyed, only transformed. If consciousness is informational in nature, then perhaps its patterns persist in some form even after biological death. This does not imply survival of identity in the traditional sense, but it raises the possibility that awareness participates in universal processes that outlast individual brains. What emerges from all these investigations is not a conclusion, but a growing set of connections. From quantum entanglement to cosmic networks, from resonance to information theory, evidence accumulates that consciousness may be linked to the universe at levels not yet understood. The parallels may be coincidental, or they may hint at an undiscovered layer of physics that binds awareness to the cosmos. Each new experiment, from telescopes mapping the farthest galaxies to quantum devices measuring the smallest particles, pushes us closer to understanding. But one question remains unresolved. Is consciousness a fleeting property of biology, destined to vanish when neurons cease firing? Or is it a reflection of the universe itself, woven into the same fabric that shapes stars, galaxies, and space-time? If consciousness is indeed woven into the same structure that governs the universe, then we must examine more closely how the brain's physical processes might interface with that deeper fabric. Neurons transmit electrical signals through ionic exchanges of sodium and potassium across cell membranes. At the simplest level, these are chemical events, measurable and repeatable, but within each neuron lies a dense scaffolding of microtubules, hollow protein structures that maintain the cell's shape and help transport materials. The Orch-Orr model proposes that these microtubules may act as quantum processors, sustaining coherent states that influence neural firing. Critics argue that decoherence would occur too quickly in the warm, wet brain for quantum effects to matter. Yet in 2013, studies of photosynthetic complexes showed quantum coherence lasting hundreds of femtoseconds in biological environments, far longer than expected. Even if microtubules cannot sustain long coherence, shorter bursts could still shape neural dynamics in ways that classical models overlook. The challenge lies in measurement. Quantum states collapse when observed, making them difficult to track. Advanced imaging techniques can measure brain activity at millisecond precision, but probing femtosecond quantum events inside neurons remains beyond current capacity. This gap leaves the field open to speculation. Some researchers suggest indirect evidence might emerge by studying anomalies in neural synchronization, subtle timing differences that classical models cannot explain. Others propose that anesthetics work by disrupting quantum states within microtubules, which could explain why consciousness shuts down while basic brain functions persist. If true, this would provide one of the first empirical links between quantum activity and subjective awareness. Stepping back to the scale of the cosmos, we encounter another parallel. The distribution of matter in the universe is not random, but follows a pattern shaped by gravity, dark matter, and expansion. Galaxies cluster along filaments separated by vast voids, creating a web-like structure across observable space. In 2020, researchers at the University of Bologna compared the cosmic web to brain networks, analyzing their statistical properties. They found striking similarities in connectivity and clustering, despite a difference in scale of 27 orders of magnitude. This does not mean the universe is a brain, but it suggests that self-organizing systems may converge on similar structures regardless of size. The implication is that information may flow through the universe in ways analogous to how it flows through neurons. This perspective aligns with theories that treat information as the bedrock of reality. Physicist John Archibald Wheeler coined the phrase "it from bit," suggesting that physical reality arises from informational choices, such as whether a photon passes through one slit or another. In this framework, the universe is fundamentally digital, built on binary yes-no decisions at the quantum level. If so, then consciousness might be both a product of information processing and a participant in it. The brain could be seen as a localized structure where the universe processes itself, creating awareness as an emergent property. The resonance between brain activity and cosmic phenomena deepens the mystery. The human brain produces oscillations across several frequency bands. Delta waves between 0.5 and 4 Hz dominate during deep sleep. Alpha waves around 8 to 12 Hz appear in relaxed states. Gamma waves above 30 Hz are linked to higher cognitive functions. These frequencies overlap with natural oscillations in the environment. The Earth's Schumann resonance resonates near 7.83 Hz, overlapping with alpha rhythms. Pulsars emit electromagnetic pulses at regular intervals, some in the same frequency ranges as human brain waves. While these correlations may be coincidental, they invite speculation about whether the brain tunes itself to environmental frequencies in ways not fully recognized. If resonance plays a role, then consciousness could involve synchronization, not just within the brain but with external systems. Physics offers many examples of synchronization, from pendulum clocks aligning their swings to fireflies flashing in unison. Large-scale synchronization emerges when systems share frequencies and interact. Could consciousness involve resonance between neural oscillations and broader electromagnetic or quantum fields? Research in magnetoencephalography shows that brain activity is sensitive to weak magnetic fields.
Some animals, such as migratory birds, clearly use magnetic cues for navigation. It is not unreasonable to ask whether human cognition may also be subtly shaped by external resonances, linking the brain to wider physical rhythms.
Artificial intelligence underscores the distinction. Modern AI can analyze terabytes of data, recognize patterns, and even simulate natural language convincingly. Yet no evidence suggests that these systems experience subjective awareness. They remain sophisticated pattern processors without inner life. This contrast raises the question of what is missing. If information processing alone produced consciousness, machines should eventually achieve it. The fact that they do not hints that human awareness depends on physical processes tied to the fabric of the universe, not just computation. Perhaps quantum effects or resonance phenomena are essential ingredients that machines built on classical hardware lack. If so, then the brain is not simply an advanced computer, but a bridge between matter and the informational foundation of reality. Death and the persistence of consciousness provide a natural test case. Neuroscience describes death as the end of organized brain activity. Electroencephalography shows brain waves fading into flat lines. The chemical and electrical processes that sustain thought cease, yet physics complicates the picture. Energy cannot be destroyed, only transformed. Information, too, may be conserved. Black hole physics suggests that information swallowed by a black hole is not lost, but encoded on its event horizon, a principle extended to the entire universe by the holographic model. If information is preserved universally, then consciousness, as an informational structure, might persist in ways we cannot yet measure. This persistence would not necessarily preserve personal identity, but it suggests that awareness may be part of a broader continuum rather than a transient spark. The implications stretch into philosophy. If the universe is informational and consciousness participates in shaping reality, then human awareness is not an isolated anomaly. It is a localized expression of universal processes. Ancient philosophies often described mind and cosmos as interconnected, but modern science now frames similar ideas in terms of networks, information, and resonance. What was once speculation gains new weight from data across physics, neuroscience, and cosmology. Still, caution remains essential. Parallels can mislead, and speculation must be grounded in evidence. The brain is not literally a miniature universe, and the universe does not literally think as a brain does, but the convergence of structures and processes across scales invites continued investigation. Each discovery, quantum coherence in biology, maps of the cosmic web, resonance between natural systems, adds pieces to a puzzle that blurs the boundary between mind and cosmos. As research advances, one question drives the exploration forward. If the brain is not merely an isolated organ but part of a larger informational fabric, then what exactly is the role of consciousness within the universe? Is it a byproduct, emerging when complexity passes a threshold? Or is it fundamental, as essential to reality as matter, energy, space, and time? The answer may redefine not only neuroscience and physics, but our very place in the cosmos. To probe this question further, it is worth examining the brain not only as a biological system, but as a dynamic processor of information interacting with its environment. Neurons fire at speeds measured in milliseconds, yet networks of them form patterns that last seconds, minutes, or even years through memory. Functional MRI studies reveal that even at rest, the brain engages in what researchers call the default mode network, a set of regions active when the mind is not focused externally. This suggests that consciousness is not just reactive, but constantly constructing an internal model of reality. If the universe is itself informational, then perhaps the brain is a specialized system designed to align with it, continuously refining its model through perception and thought. The interplay between perception and reality becomes clear in studies of time. Neuroscience shows that subjective time depends on attention. In experiments, participants asked to focus intently on stimuli often report longer durations than objective clocks measure. Conversely, routine tasks compress time perception, making hours feel like minutes. At the quantum level, the problem of time is even stranger. Equations describing quantum states, such as the Schrödinger equation, do not require time as we experience it. In relativity, time is tied to motion and gravity, stretching and compressing depending on speed and mass. If human time perception differs from physical time, then consciousness might act as a bridge, translating timeless quantum states into lived experience. The brain could be where physics acquires subjective flow, turning probability into narrative. Another frontier is memory storage. Classical neuroscience ties memory to synaptic plasticity, where repeated firing strengthens neural pathways. Yet this model struggles to explain the precision and longevity of certain memories. Some studies suggest electromagnetic fields generated by neural firing could help maintain patterns beyond chemical changes. This aligns with broader theories that information in the brain is both local in synapses and distributed in fields. If fields are involved, then memory may not be fully confined to neurons. It might extend into electromagnetic or even quantum domains. Such a view would place human recollection within the same informational continuum that governs stars, particles, and galaxies. The unknown substances of the universe amplify these mysteries. Dark matter and dark energy together account for about 95% of the cosmos, yet remain undetected except through indirect effects. If most of reality is hidden, then our models of consciousness may also be incomplete. The possibility exists that unknown forms of matter or energy interact with cognition. While no evidence currently supports this, the analogy between invisible dark matter shaping galaxies and invisible consciousness shaping human behavior is compelling. Both act through influence rather than direct observation. Both remain unmeasured in essence, and both dominate their domains. Resonance once again emerges as a common thread. Human brainwaves synchronize during collective activities such as music, meditation, or group problem solving. Studies using electroencephalography show that people engaged in cooperative tasks often display interbrain synchrony. Resonance here is not metaphorical, but measurable, linking individuals into temporary networks of shared rhythm. In physics, resonance governs how atoms bond, how stars oscillate, and how gravitational waves ripple through space. This suggests that resonance is not confined to one scale or system, but is a principle that links systems across the universe. Consciousness may therefore not only emerge within brains, but also synchronize between them, hinting at a larger fabric of awareness. Artificial intelligence provides a crucial counterpoint. Despite rapid progress in machine learning, no system has yet displayed signs of self-awareness. Neural networks in computers process inputs, generate outputs, and even simulate creativity, but all evidence suggests they lack subjective experience. This highlights the difference between information processing and consciousness. If machines with billions of parameters cannot feel, then consciousness requires more than computation. It may require the specific physical substrate of biological brains, perhaps even their quantum or field-level dynamics. This would explain why human awareness feels irreducible to code. It also raises questions about whether machines could ever bridge the gap, or whether consciousness is exclusive to systems embedded in the physical laws of the universe in particular ways. Death forces the issue to its sharpest point. Brain death is defined as the irreversible cessation of neural activity, yet reports of near-death experiences, while anecdotal, raise questions about how consciousness persists in altered states. From a physics perspective, energy dissipates, but information may not vanish. Black hole paradoxes show the struggle to reconcile conservation of information with relativity and quantum mechanics. If information is conserved universally, then the patterns that constitute consciousness might be preserved in some form. They may not remain as coherent identity, but they may persist as part of the informational field of the cosmos. This perspective reframes death not as absolute cessation, but as transformation, the one beyond current measurement. Information itself may be the key. Increasingly, scientists view information not just as data, but as a physical entity. Entropy, a measure of disorder, is fundamentally about information loss. Quantum mechanics treats particles as carriers of information about probabilities. Cosmology frames the universe as an information processing system, evolving complexity over time. If consciousness is informational, then it is not a separate essence, but a pattern within the same field that shapes galaxies, black holes, and atomic interactions. The brain is simply one highly complex node where the universe reflects upon itself. Yet one question remains: why does consciousness feel like something from within? If it is only information, why should there be subjective awareness at all? This is the unresolved hard problem. It may be that awareness is fundamental, not derived, just as mass, charge, and spin are irreducible properties of matter. Consciousness may be an irreducible property of information. If so, then every interaction at some level carries a faint echo of awareness, becoming fully realized only when complexity passes a threshold. This would place consciousness alongside gravity and electromagnetism as a basic feature of reality. The search continues through experiments at both extremes. Quantum physicists build ever more delicate systems to probe entanglement, coherence, and measurement. Neuroscientists map brain circuits with increasing precision, seeking the neural correlates of consciousness. Cosmologists chart the universe, tracing its vast networks and hidden matter. Each field contributes fragments, but together they suggest that consciousness and cosmos may not be separate domains. They may be facets of the same reality viewed from different scales. As evidence grows, so does the need for humility. The parallels between brain and universe could be coincidence, or they could point toward a deeper law. Either way, the questions are unavoidable. If consciousness emerges from quantum interactions, what does that reveal about the role of observers in shaping reality? If the brain and the cosmic web share structural laws, does that mean awareness is a universal pattern? If information cannot be destroyed, does consciousness persist beyond death in some form? Each possibility forces us to reconsider assumptions about mind, matter, and the universe. Perhaps the true mystery is not whether the brain is connected to the universe, but how deeply that connection runs. Does consciousness simply mirror universal processes, or is it integral to them? Could awareness be the universe's way of perceiving itself? Or is it only a fleeting local phenomenon destined to vanish when neurons go silent? The search for answers continues, guided by data, challenged by paradox, and driven by the oldest question of all: what is the nature of the mind within the cosmos? The question of consciousness, when viewed against the backdrop of the universe, may be among the most mysterious puzzles humanity has ever faced. Scientists, philosophers, and mystics alike have wondered whether the brain is merely a biological machine producing awareness, or whether it is instead a receiver tuned to deeper currents of reality. When we explore this frontier, the boundary between neuroscience and cosmology begins to blur, suggesting that the mind and the cosmos may not be separate after all. To probe this question further, it is worth examining the brain not only as a biological system, but as a dynamic processor of information interacting with its environment. Neurons fire at speeds measured in milliseconds, yet networks of them form patterns that last seconds, minutes, or even years through memory. Functional MRI studies reveal that even at rest, the brain engages in what researchers call the default mode network, a set of regions active when the mind is not focused externally. This suggests that consciousness is not just reactive, but constantly constructing an internal model of reality. If the universe is itself informational, then perhaps the brain is a specialized system designed to align with it, continuously refining its model through perception and thought. The interplay between perception and reality becomes clear in studies of time. Neuroscience shows that subjective time depends on attention. In experiments, participants asked to focus intently on stimuli often report longer durations than objective clocks measure. Conversely, routine routine tasks compress time perception, making hours feel like minutes. At the quantum level, the problem of time is even stranger. Equations describing quantum states, such as the Schrödinger equation, do not require time as we experience it. In relativity, time is tied to motion and gravity, stretching and compressing depending on speed and mass. If human time perception differs from physical time, then consciousness might act as a bridge, translating timeless quantum states into lived experience. The brain could be where physics acquires subjective flow, turning probability into narrative. Another frontier is memory storage. Classical neuroscience ties memory to synaptic plasticity, where repeated firing strengthens neural pathways. Yet this model struggles to explain the precision and longevity of certain memories. Some studies suggest electromagnetic fields generated by neural firing could help maintain patterns beyond chemical changes. This aligns with broader theories that information in the brain is both local in synapses and distributed in fields. If fields are involved, then memory may not be fully confined to neurons. It might extend into electromagnetic or even quantum domains. Such a view would place human recollection within the same informational continuum that governs stars, particles, and galaxies. The unknown substances of the universe amplify these mysteries. Dark matter and dark energy together account for about 95% of the cosmos, yet remain undetected except through indirect effects. If most of reality is hidden, then our models of consciousness may also be incomplete. The possibility exists that unknown forms of matter or energy interact with cognition. While no evidence currently supports this, the analogy between invisible dark matter shaping galaxies and invisible consciousness shaping human behavior is compelling. Both act through influence rather than direct observation, both remain unmeasured in essence, and both dominate their domains. Resonance once again emerges as a common thread. Human brainwaves synchronize during collective activities such as music, meditation, or group problem solving. Studies using electroencephalography show that people engaged in cooperative tasks often display interbrain synchrony. Resonance here is not metaphorical, but measurable, linking individuals into temporary networks of shared rhythm. In physics, resonance governs how atoms bond, how stars oscillate, and how gravitational waves ripple through space. This suggests that resonance is not confined to one scale or system, but is a principle that links systems across the universe. Consciousness may therefore not only emerge within brains, but also synchronize between them, hinting at a larger fabric of awareness. Artificial intelligence provides a crucial counterpoint. Despite rapid progress in machine learning, no system has yet displayed signs of self-awareness. Neural networks in computers process inputs, generate outputs, and even simulate creativity, but all evidence suggests they lack subjective experience. This highlights the difference between information processing and consciousness. If machines with billions of parameters cannot feel, then consciousness requires more than computation. It may require the specific physical substrate of biological brains, perhaps even their quantum or field-level dynamics. This would explain why human awareness feels irreducible to code. It also raises questions about whether machines could ever bridge the gap, or whether consciousness is exclusive to systems embedded in the physical laws of the universe in particular ways. Death forces the issue to its sharpest point. Brain death is defined as the irreversible cessation of neural activity, yet reports of near-death experiences, while anecdotal, raise questions about how consciousness persists in altered states. From a physics perspective, energy dissipates, but information may not vanish. Black hole paradoxes show the struggle to reconcile conservation of information with relativity and quantum mechanics. If information is conserved universally, then the patterns that constitute consciousness might be preserved in some form. They may not remain as coherent identity, but they may persist as part of the informational field of the cosmos. This perspective reframes death not as absolute cessation, but as transformation, though one beyond current measurement. Information itself may be the key. Increasingly, scientists view information not just as data, but as a physical entity. Entropy, a measure of of disorder is fundamentally about information loss. Quantum mechanics treats particles as carriers of information about probabilities. Cosmology frames the universe as an information processing system, evolving complexity over time. If consciousness is informational, then it is not a separate essence, but a pattern within the same field that shapes galaxies, black holes, and atomic interactions. The brain is simply one highly complex node where the universe reflects upon itself. Yet one question remains: why does consciousness feel like something from within? If it is only information, why should there be subjective awareness at all? This is the unresolved hard problem. It may be that awareness is fundamental, not derived. Just as mass, charge, and spin are irreducible properties of matter, consciousness may be an irreducible property of information. If so, then every interaction at some level carries a faint echo of awareness, becoming fully realized only when complexity passes a threshold. This would place consciousness alongside gravity and electromagnetism as a basic feature of reality. The search continues through experiments at both extremes. Quantum physicists build ever more delicate systems to probe entanglement, coherence, and measurement. Neuroscientists map brain circuits with increasing precision, seeking the neural correlates of consciousness. Cosmologists chart the universe, tracing its vast networks and hidden matter. Each field contributes fragments, but together they suggest that consciousness and cosmos may not be separate domains. They may be facets of the same reality viewed from different scales. As evidence grows, so does the need for humility. The parallels between brain and universe could be coincidence, or they could point toward a deeper law. Either way, the questions are unavoidable. If consciousness emerges from quantum interactions, what does that reveal about the role of observers in shaping reality? If the brain and the cosmic web share structural laws, does that mean awareness is a universal pattern? If information cannot be destroyed, does consciousness persist beyond death in some form? Each possibility forces us to reconsider assumptions about mind, matter, and the universe. Perhaps the true mystery is not whether the brain is connected to the universe, but how deeply that connection runs. Does consciousness simply mirror universal processes, or is it integral to them? Could awareness be the universe's way of perceiving itself? Or is it only a fleeting local phenomenon, destined to vanish when neurons go silent? The search for answers continues, guided by data, challenged by paradox, and driven by the oldest question of all: what is the nature of the mind within the cosmos? If consciousness is indeed entangled with the laws of physics, the question arises of how such entanglement could be measured. One avenue is the study of microtubules, cylindrical structures within neurons that guide cellular processes. In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that microtubules might support quantum coherence inside the brain, giving rise to consciousness. Their ORC-OR model suggested that quantum events collapse in ways shaped by gravity, embedding awareness within the fabric of space-time itself. While controversial, this theory pushed neuroscience beyond synapses into the quantum scale, where computation and physics intertwine. Critics argue that the warm, wet environment of the brain would prevent fragile quantum states from persisting, yet newer studies of quantum biology complicate this objection. Photosynthesis in plants, for instance, uses quantum coherence to transfer energy efficiently even in complex molecular environments. Birds appear to navigate using quantum effects in their eyes, sensing Earth's magnetic field. If such coherence can exist in biological systems, the possibility remains open that the brain too might sustain it. Experiments have begun probing these limits. Researchers have detected entanglement in diamond impurities at room temperature, suggesting that certain structures can preserve quantum information despite thermal noise. Microtubules, with their ordered lattices, may function similarly. Some laboratory tests show resonance frequencies within microtubules, hinting they may store or process information beyond classical chemical interactions. If confirmed, this would mean that thought is not just electrical but quantum mechanical. The implications are profound. It would suggest that each act of perception is not merely the firing of neurons, but the resolution of quantum probabilities, linking human awareness to the deepest structures of reality. At the same time, mainstream neuroscience cautions against overextending these ideas. Much of brain function can be explained by classical processes. Neurons integrate signals, generate spikes, and adjust synapses based on experience. Models of learning and decision-making operate successfully without invoking quantum physics. Yet, classical explanations leave the hard problem unresolved. Why does subjective experience arise at all? It is here that quantum theories find their foothold, not by displacing classical neuroscience, but by supplementing it. Consciousness may require both levels, just as chemistry requires both atomic physics and molecular interactions. Looking outward to the cosmos provides another line of evidence. The universe itself displays quantum behavior on massive scales. Black holes, once thought to be perfect absorbers, appear to radiate energy through quantum processes, a phenomenon known as Hawking radiation. This means that information, even at the edge of collapse, cannot simply vanish. The paradox of information loss in black holes remains unsolved, yet it echoes the question of whether consciousness information can vanish at death. If cosmic laws preserve information, then perhaps the patterns that constitute awareness also find ways to persist, even if not in recognizable form. The symmetry between universal and neural puzzles suggests a shared framework waiting to be uncovered. Mathematics offers another clue. Studies comparing large-scale simulations of the cosmic web to networks of brain cells reveal striking structural similarities. In both, about 70% of connections are short-range, while 30% span longer distances, forming a balance between local clusters and global integration. This architecture supports both stability and communication, whether between galaxies or neurons. The resemblance is more than visual. It reflects similar rules of network efficiency. Both systems maximize connectivity while minimizing energy costs. If the universe and the brain follow the same network principles, then consciousness may not be a local accident but part of a universal design for complexity. The role of the observer also demands attention. Quantum mechanics shows that measurement influences outcome. In the famous double-slit experiment, particles act as waves when unobserved, but collapse into definite states when measured. Some interpretations suggest that consciousness itself is what causes collapse. Others argue measurement does not require awareness, only interaction. Yet the debate highlights the centrality of observation. If consciousness is tied to measurement, then every act of awareness is a quantum event, shaping reality at fundamental levels. This would mean the universe is not fully real without observers, and that minds are woven into the fabric of physics. The potential link between cosmic expansion and cognitive expansion is also striking. Roughly 13.8 billion years ago, the universe began in the Big Bang, expanding ever since. Similarly, the brain develops from a single fertilized cell into trillions of connections over decades. Both follow principles of self-organization, generating complexity from simple origins. Cosmology identifies inflation, dark energy, and gravitational clustering as drivers of universal growth. Neuroscience identifies synaptic pruning, plasticity, and network integration as drivers of cognitive growth. The parallel is not exact, but suggests a shared trajectory. Matter and mind evolve toward increasing complexity and awareness. The possibility arises that consciousness is not accidental, but inevitable once complexity reaches critical thresholds. This speculation finds support in information theory. Claude Shannon, in 1948, defined information as reduction of uncertainty. The brain reduces uncertainty by predicting sensory inputs, constantly testing models against reality. The universe, too, evolves by reducing uncertainty, collapsing quantum probabilities into definite outcomes. At both scales, reality advances through information processing. If so, consciousness may be the most refined expression of this principle, the apex of informational evolution. Humans are not separate from the universe, but one of its methods for knowing itself. Still, mysteries remain. Near-death studies, altered states of consciousness, and reports of collective awareness hint at dimensions beyond current science. While empirical validation is lacking, the persistence of such phenomena across cultures suggests they touch on real aspects of human experience. If consciousness is indeed connected to the universe, then extraordinary states may reveal its wider scope. Investigating them with rigor rather than dismissal may provide missing pieces of the puzzle. The quest to unify quantum mechanics and general relativity also intersects here. Physicists seek a theory of everything, yet the role of consciousness is rarely addressed in such frameworks. Could it be that the final unification requires acknowledging awareness as a fundamental element? If space-time, matter, energy, and information are all basic, then consciousness may belong on the same list. Ignoring it risks leaving out a crucial part of reality, including it may demand new mathematics, new physics, and new philosophy. The brain, then, is not just an organ within a skull. It is a system resonating with universal laws, mirroring cosmic structures, and possibly participating in quantum events that define existence itself. Each thought may be a small act of alignment with the fabric of reality. Each memory may be a trace of information preserved within the same laws that conserve galaxies. Each act of awareness may be the universe becoming aware of itself. But if this is so, what comes next? Does advancing neuroscience eventually uncover the full mechanism of consciousness, reducing mystery to equation? Or will every discovery only deepen the paradox, showing us more of the mirror without revealing what lies behind it? Could consciousness be both local and universal, both emergent and fundamental? And if so, what does that imply about our place within the cosmos? The deeper scientists probe into the mysteries of matter, the more they find that information may be as fundamental to reality as mass and energy. At the quantum level, every particle can be described by a set of informational properties, position, spin, momentum, charge, that define its state. When interactions occur, this information is exchanged, conserved, or transformed, but never destroyed. Physicists studying quantum entanglement have shown that two particles can share informational states even when separated by vast distances, behaving as if they remain one system. This phenomenon suggests that the universe is not a collection of isolated objects, but an informational web where connections matter as much as components. When applied to the brain, the concept takes on new weight. Neurons communicate not just by firing or remaining silent, but by patterns of timing, frequency, and synchronization. These patterns constitute codes of information that shape perception and decision-making. Electroencephalography reveals waves of activity rippling through the brain, sometimes localized, sometimes sweeping across hemispheres. These oscillations resemble information broadcasts, ensuring that distant regions remain aligned. Consciousness may emerge when enough information becomes globally available across the brain, allowing a unified sense of self and experience. This is known as the global workspace theory, and it aligns with computational principles. Yet it raises further questions about how and why information crossing a threshold should feel like awareness. In cosmology, large-scale surveys of galaxies show that matter organizes into filaments and nodes, forming a cosmic web. Computer simulations of this structure reveal that information about initial conditions, the density fluctuations present in the first few 100,000 years after the Big Bang, determines the shape of galaxies billions of years later. The present universe is thus a memory of its earliest moments, encoded into its very structure. If the cosmos is shaped by information carried forward across time, then the analogy with memory in the brain becomes sharper. Just as neural patterns preserve past experiences to guide future behavior, cosmic patterns preserve primordial conditions to guide the evolution of galaxies. In both cases, information is not passive but active, steering complexity forward. The question then becomes whether consciousness is best understood as an informational process, one that extends beyond the brain. If information is woven into the universe itself, then consciousness may not arise from neurons alone, but from their capacity to harness universal informational laws. The brain could be seen as a biological interface, decoding and encoding information embedded in reality. In this view, awareness is not a separate essence, but a process of alignment, similar to how a radio tunes into frequencies already present in the environment. Experiments exploring consciousness often return to the limits of measurement. The double-slit experiment remains one of the clearest demonstrations that observation alters outcomes. Photons or electrons create an interference pattern when unmeasured, behaving as waves, but when detectors are placed to observe their path, the interference disappears and particles behave as if they chose a definite trajectory. The act of measurement collapses probabilities into facts. Whether consciousness is necessary for this collapse remains debated, but the parallels are striking. Each conscious act of perception may be a similar collapse, resolving uncertainty into experience. In this sense, awareness could be thought of as the universe's mechanism for selecting realities from a field of potential. Neuroscience adds nuance to this perspective. Studies of predictive processing suggest that the brain constantly generates models of reality and tests them against sensory input. Perception is not raw reception, but an active hypothesis confirmed or adjusted moment by moment. This aligns neatly with the idea of collapsing probabilities. Just as a quantum wave function reduces to a definite state upon observation, the brain's models reduce to perceptual experience upon confirmation. Consciousness may therefore be the experience of participating in this process, where informational probabilities become lived reality. The boundary between physics and neuroscience grows thinner in discussions of energy efficiency. The brain, despite consuming only about 20 watts, performs computations that would overwhelm today's most powerful supercomputers. It achieves this through massively parallel processing, intricate coding strategies, and perhaps mechanisms not yet fully understood. Similarly, the universe evolves with remarkable efficiency, producing complexity from relatively simple laws. Both systems suggest that there is an optimal way for information to self-organize, one that maximizes output while minimizing energy expenditure. Identifying these principles may reveal why consciousness exists at all. Perhaps it is the most efficient way for information to be integrated and utilized. The persistence of information in physics also invites speculation about what happens when the brain ceases to function. In quantum mechanics, information cannot be destroyed, only transformed. In black hole physics, the debate over whether information is lost during collapse led to the development of the holographic principle, which proposes that the information content of a region of space can be encoded on its boundary. If similar laws apply universally, then perhaps the informational patterns that constitute consciousness are also preserved in some form even after biological processes end. They may not persist as personal identity, but could contribute to the informational field of the universe, woven back into the larger fabric from which they emerged. Biology provides smaller-scale examples of how information transcends individual systems. DNA encodes instructions across generations, ensuring continuity of life. Cultural knowledge, transmitted through language, persists far longer than individual lifespans. These examples show that patterns of information can survive the systems that host them. Consciousness, too, may generate patterns, through memory, through interaction, through resonance, that ripple outward, leaving traces beyond the individual. If so, awareness is not entirely confined to the skull, but part of a larger informational ecology, interacting with and shaping its environment in lasting ways. Another domain of evidence comes from collective synchronization. Studies of group meditation, musical performance, or coordinated activity show measurable coherence between brainwaves of participants. Functional imaging reveals that social interaction can align neural patterns, creating temporary states of shared rhythm. This is not merely metaphorical, it is quantifiable synchrony, as if multiple minds resonate into a larger network. On cosmic scales, resonance governs the behavior of matter from atomic bonds to planetary orbits. The recurrence of this principle across scales suggests that synchronization is a universal mechanism for generating coherence. Consciousness may therefore not be limited to individuals but may scale outward, aligning multiple observers into shared states of awareness. Yet, despite these connections, a crucial challenge remains. Why is there something it feels like to be conscious? Information alone does not explain subjective experience, the first-person perspective that distinguishes awareness from computation. Philosophers call this the hard problem. Even if we can map the informational flows in the brain and the cosmos, why those flows should produce sensation is unclear. Some propose that consciousness is a fundamental property of reality, as intrinsic as space, time, and energy. In this framework, every informational process carries some degree of awareness, with the human brain providing the complexity necessary to integrate it into rich experience. Others resist this view, insisting consciousness must eventually be explained by emergent properties of physical processes. The debate remains open, but the stakes are high. If awareness is fundamental, then the universe is not unconscious matter, but a field where experience pervades at every scale. This speculation carries implications beyond science. If consciousness is woven into the universe, then human awareness is not isolated but continuous with the cosmos. It would mean that every thought is both a private event and a universal one, echoing within the informational fabric that underlies all things. It suggests that observing the universe is not a detached act, but a participation in its unfolding. Each measurement, each perception, each memory becomes part of the larger process through which the cosmos evolves. But can this be tested? Could experiments one day confirm that consciousness interacts directly with quantum states, that awareness has measurable effects on the physical world? Or will consciousness always elude precise definition, remaining a frontier where science meets philosophy? The search continues, driven by the recognition that to understand the universe fully, we must also understand ourselves. If the brain can be seen as an interface with universal information, then the question arises of how this interface operates across scales of size and energy. The human skull encloses roughly 1.5 liters of tissue, a relatively small volume compared to the scale of the universe. Yet within this space is packed over 86 billion neurons and perhaps 100 trillion synapses. Each connection transmits electrical and chemical signals, but more importantly, it shapes probability, deciding which pathways fire and which remain silent. On this basis alone, the brain resembles a microcosm of the universe, countless components, interactions governed by rules, emergent complexity arising from the sum. But the critical point is that these interactions are not random. They are structured, constrained, and organized by laws that maximize efficiency. In the cosmos, gravity shapes matter into stars and galaxies. In the brain, plasticity shapes neural circuits into memory and thought. Both are sculpted by forces that give order to otherwise chaotic systems. Consider the example of synchronization. In astrophysics, the rotation of moons often becomes locked in resonance with their planets, as seen with Earth's moon, which shows the same face to us because its orbital and rotational periods match. In neuroscience, the principle of phase locking describes how groups of neurons can synchronize their firing to external rhythms, such as music or speech. The brain and the cosmos thus rely on synchronization to generate stability across vast differences of scale. When systems synchronize, they create coherence, and coherence in turn allows higher forms of organization. This principle may lie at the heart of consciousness itself. Coherence across networks may generate the unified field we experience as awareness. The search for coherence within the brain is not purely theoretical. Magnetoencephalography, which measures the tiny magnetic fields produced by neural currents, shows that oscillations at particular frequencies, alpha, beta, gamma, emerge during different states of awareness. Gamma waves above 30 Hz appear during moments of focused attention or problem solving, when distributed networks must integrate into a single cognitive act. In this sense, consciousness could be seen as the alignment of billions of neurons into coherent resonance, much like galaxies align into structures under the influence of gravity. If so, then awareness is not localized to any one neuron, but arises from the global coherence of the whole system. The parallel deepens when considering the storage of information. The universe records its history in the distribution of galaxies, the cosmic microwave background radiation, and the chemical composition of stars. Each element heavier than hydrogen and helium was forged in earlier generations of stars, which exploded and spread their products through space. Every atom of iron in human blood was once produced in the core of a supernova billions of years ago. The universe thus remembers through matter itself. The brain similarly encodes memory in synaptic weights, structural changes, and possibly field dynamics. Both systems show that information is not abstract but embodied, written into the fabric of reality, whether in matter, energy, or neural architecture. This brings us to the question of whether the brain can influence the universe beyond its biological limits. Psychologists study phenomena such as the placebo effect, where expectation alters physical outcomes, demonstrating that belief and mental states can shape physiology. Some speculative experiments have attempted to test whether human intention can influence random number generators, with controversial results. While mainstream science remains cautious, the question lingers: if consciousness is truly connected to quantum processes, might awareness subtly affect probability at the smallest scales? If true, then the brain would not only reflect the universe but participate in shaping it, however faintly. The role of scale must be considered carefully. Quantum events occur at dimensions measured in nanometers and femtoseconds, while cosmic structures stretch across billions of light years. The brain operates between these extremes, yet touches both. It is built of quantum particles but experiences macroscopic time and space. This middle position may allow it to translate between scales, a mediator between micro and macro. Some theorists suggest that this translation is precisely what consciousness is, the transformation of quantum probability into classical perception, binding the smallest elements of reality to the largest. Experiments with quantum computing provide a useful analogy. Quantum computers, though still in their early stages, exploit superposition and entanglement to perform calculations that classical systems cannot. Their power comes not from speed alone, but from harnessing quantum information directly. If the brain does something similar, then consciousness may be the natural outcome of biological quantum computation. Unlike artificial quantum devices, however, the brain integrates this computation with emotion, memory, and sensory processing, producing lived experience rather than abstract output. One challenge to this view is decoherence, the tendency for quantum states to collapse in warm, noisy environments. Critics argue that the brain is far too noisy for delicate quantum processes to persist. Yet evidence from quantum biology suggests otherwise. Photosynthetic complexes maintain coherence long enough to transfer energy efficiently. Enzymes may use quantum tunneling to accelerate reactions. Even olfaction may involve quantum processes in scent detection. These findings undermine the assumption that quantum effects cannot exist in biology, opening the door for similar processes in neural systems. If so, then consciousness could indeed be grounded in quantum coherence, protected or exploited by microtubules or other cellular structures. Beyond physics and biology, philosophy must grapple with the implications. If consciousness is not confined to the brain but linked to the universe, then the traditional separation between subject and object intellect weakens. Awareness becomes not a private glow inside the skull, but a phenomenon continuous with reality itself. This perspective resembles certain strands of panpsychism, which hold that consciousness is fundamental and pervasive, varying in degree with complexity. While controversial, such views are gaining attention as neuroscience and physics confront the limits of reductionism. To reduce consciousness solely to neurons or atoms may miss the point, just as reducing life solely to chemistry misses the organizational principles that distinguish living systems from inert matter. This shift also has consequences for how humans see themselves. If the brain is connected to the universe, then human awareness is not an anomaly, but part of the cosmic order. The sense of isolation that often accompanies modern scientific thought, humans as small figures in an indifferent cosmos, may give way to a recognition of deep continuity. The same laws that shape galaxies also shape thought. The same information that governs particles also underlies memory. Consciousness is not outside of physics, but within it, as integral as energy or entropy. Yet the question remains, does the universe require consciousness to exist, or does consciousness simply emerge from it? Quantum interpretations diverge sharply here. The Copenhagen interpretation suggests measurement collapses probabilities, leaving room for speculation about the role of awareness. The many worlds interpretation eliminates collapse, positing that all probabilities unfold in branching realities regardless of observation. If the latter is true, consciousness does not determine reality but navigates through it. In either case, awareness remains entangled with the structure of existence, shaping or selecting pathways through the infinite field of possibility. What emerges from this exploration is not certainty, but a landscape of possibilities. The brain, through its complexity, may resonate with cosmic structures, harness quantum effects, and encode information in ways that parallel the universe itself. Whether this means consciousness is fundamental, emergent, or both is still unknown. But the parallels cannot be ignored. They suggest that by studying the brain, we are also studying the cosmos. And by studying the cosmos, we are also studying ourselves. And so the unresolved question grows sharper. If the brain is truly a reflection of the universe, could it also be a gateway into understanding dimensions of reality we have yet to perceive? If consciousness is indeed interwoven with the universe, then perhaps the next mystery is not how it exists, but why. Evolutionary biology often explains the brain as an adaptive organ designed to process information for survival, to detect predators, to locate food, to navigate complex social worlds. Yet this explanation accounts only for function, not for the phenomenon of subjective experience. Why should survival require an inner world of awareness rather than mere reflex and reaction? Why should the universe give rise to beings that not only exist, but also know they exist? This puzzle has been called the hard problem of consciousness. Philosophers distinguish between the mechanics of cognition, the so-called easy problems of perception, memory, and decision, and the enigma of subjective feeling. A bat navigating by echolocation or a human savoring music experiences a quality beyond the firing of neurons. Physics may chart the flow of energy and information, but the leap from data to lived experience remains obscure. If the brain is a mirror of the universe, then perhaps consciousness is not an evolutionary accident, but a principle woven into reality itself. Consider the night sky. For billions of years, galaxies swirled, stars burned, and planets formed in silence. Yet only when life emerged did the cosmos become self-aware. Through human eyes, the universe now observes itself. Through human thought, it questions its own origin. Through human imagination, it speculates about its own destiny. This reflexive loop, universe perceiving universe, suggests that consciousness may be the ultimate product of cosmic evolution. In this sense, the brain is not merely an organ, but a lens through which existence studies its own patterns. Scientific metaphors abound. The laws of thermodynamics describe entropy, the tendency for systems to drift toward disorder. Yet consciousness appears to resist this pull, gathering scattered data into coherent order. A mind can take billions of sensory signals per second, and unify them into the seamless illusion of reality. Memory integrates past with present, imagination projects future possibilities, and identity stitches these together into the sense of self. This ordering mirrors the structure of galaxies condensing from gas or stars forming from dust clouds. In both brain and cosmos, order emerges from chaos and coherence emerges from randomness. Could the laws that sculpt stars also sculpt awareness? Astrophysicists often speak of the fine-tuning problem, the fundamental constants of physics, the strength of gravity, the charge of the electron, the rate of cosmic expansion, are all precisely set within narrow ranges. Even slight deviations would have prevented the formation of matter, stars, or life. Why the universe should possess such delicately balanced parameters remains unknown. Some propose multiverse theories, others hint at deeper principles. But the fact remains, the universe allows complexity, and complexity allows consciousness. The fine-tuning of physical laws may not only permit existence, but also invite awareness. Parallel mysteries exist within the brain. Neural development follows a blueprint encoded in DNA, yet no gene specifies consciousness directly. Instead, countless molecular interactions unfold into structured layers, circuits, and networks that somehow give rise to mind. This orchestration is astonishingly precise, and small errors can disrupt the entire system. Just as the cosmos appears fine-tuned for life, the brain appears fine-tuned for awareness. The symmetry between these two levels suggests a continuity of principle, though the mechanism remains elusive. Cultural traditions long intuited such connections. Ancient philosophies from India spoke of Atman and Brahman, the self and the cosmic totality, as reflections of one another. Mystics across civilizations described experiences of unity in which the boundary between self and world dissolved. Modern neuroscience sometimes studies these altered states through meditation research, noting decreased activity in brain regions that regulate self-other distinctions. While science explains the mechanism, the subjective experience echoes an ancient insight that consciousness may not be confined to the individual, but part of a universal field. Even the symbols we create reflect this intuition. Artists paint spirals resembling galaxies, yet also echoing the coils of DNA or the whirls of fingerprints. Sacred architecture often mirrors cosmic order. The dome of a temple like the dome of the sky, the axis of a pyramid pointing towards stars. These patterns hint at an unconscious recognition. The microcosm and macrocosm are bound. The brain, in imagining the universe, cannot help but shape its visions in its own likeness. Yet the question deepens. If consciousness is linked to the universe, what lies beyond human awareness? Could there be levels of consciousness inaccessible to the brain, just as the visible spectrum is only a fraction of electromagnetic radiation? Perhaps our minds are tuned to survival frequencies, filtering reality to what is useful, not to what is total. Cognitive scientists speak of attention as a bottleneck. From infinite stimuli, we perceive only a narrow channel. But if consciousness extends beyond the brain, then perhaps awareness exists on scales we cannot yet measure, planetary, stellar, or even cosmic consciousness. Though speculative, such possibilities challenge the assumption that human awareness is the peak of experience. This possibility forces us to revisit an unsettling thought. What if the universe itself is alive in some way? Not in the biological sense, but as a dynamic system with properties of self-organization, adaptation, and perhaps even awareness. Some astrophysicists entertain the idea of a living cosmos, where matter and energy form evolving structures with feedback loops resembling metabolism. The Gaia hypothesis, originally describing Earth's biosphere as a self-regulating system, could in principle extend to larger scales. If Earth can maintain equilibrium conducive to life, could the cosmos itself maintain conditions conducive to consciousness? Modern technology may bring us closer to answers. Artificial intelligence and brain-machine interfaces already blur the line between biology and computation. As machines simulate neural networks and even model consciousness, they provide experimental platforms to test theories of awareness. If an artificial system ever demonstrates genuine subjective experience, it may reveal that consciousness is not limited to organic brains but is a property of complex systems more generally. This would echo the idea that consciousness, like gravity or electromagnetism, is a fundamental aspect of the universe, emerging wherever conditions allow. Still, caution is necessary. The human brain remains the only known seat of consciousness, and its mysteries are far from solved. Each discovery, quantum coherence, neural oscillations, fine-tuning, raises more questions than answers. The parallels between brain and universe may be profound or may be illusions shaped by human pattern seeking. Yet even if symbolic, they guide inquiry, pushing science and philosophy toward deeper integration. At the frontier, we face an unresolved paradox. If consciousness is simply a product of physical processes, then it should be fully explainable by neuroscience and physics. Yet no such explanation has closed the gap between matter and mind. If instead consciousness is fundamental, then the universe itself may be sentient at some level. But this idea challenges the material foundations of science. Between these poles lies the unknown, a mystery as vast as the cosmos and as intimate as thought. And so we return to the central question with which this journey began. Is the brain merely a biological machine that simulates awareness, or is it a doorway through which the universe itself becomes conscious? Underneath the surface of measurable science lies an equally enduring curiosity, the possibility that patterns within the human brain and the structure of the cosmos are not coincidental but reflect a hidden order. To explore this, we must step into the domain of synchronicity, where events that appear unrelated line up in ways too precise to dismiss as mere chance. Carl Jung, in the early 20th century, described synchronicity as meaningful coincidence. While his ideas were psychological rather than physical, modern research on probability and pattern detection has begun to ask whether there is something deeper at play. Statistically, coincidences are inevitable. In a world of billions of people and countless daily events, improbable overlaps are bound to happen. Two strangers meeting with the same birthday, a thought arriving just before a phone call, or dreams aligning with real-world events, all can be explained as statistical clustering. Yet the human brain resists reducing such moments to numbers. It assigns meaning. That search for meaning may reveal something more fundamental, that the brain itself has evolved to detect correlations. And those correlations may be tuned not only to survival, but also to larger rhythms of nature and even the universe. Physics introduces another possibility. In quantum mechanics, correlations across distance occur not by causal connection, but by entanglement. Two particles, no matter how far apart, can behave as if they share a single state. What if the brain, operating at scales where quantum effects matter, participates in a web of correlations larger than itself? In this view, synchronicity is not random, but a glimpse into hidden connections at the quantum level. Experiments in 2017 measuring brain activity during entanglement simulations found unusual coherence patterns in EEG signals, hinting, though not proving, that human thought might align with entangled systems. Such findings are preliminary, but they encourage exploration of the brain as more than an isolated system. Beyond the laboratory, synchronicity often appears in the natural world. Seasonal migrations of birds align with magnetic fields. Plants release pollen in cycles linked to lunar phases. Circadian rhythms in humans synchronize with the Earth's rotation, even in the absence of external light cues. These are not coincidences, but evidence that life systems are tuned to cosmic rhythms. The human brain, built from the same matter and subjected to the same cycles, may also be entrained to patterns beyond immediate perception. When we notice coincidences, we may be registering subtle alignments with these broader cycles. Consider the Schumann resonances, electromagnetic frequencies generated by lightning discharges circling the Earth, resonating at around 7.83 Hz. Curiously, this frequency falls within the range of human alpha brainwaves associated with calm states and meditation. While correlation does not prove causation, studies have found intriguing synchronicities between global lightning activity and shifts in collective human behavior. This raises a provocative question. Could consciousness be influenced by planetary scale frequencies, with the brain acting as a receiver in addition to a generator? Cultural traditions anticipated such possibilities long before scientific instruments existed. Ancient Arab scholars, for example, studied celestial alignments not only for navigation but also for patterns of meaning. Astrology, though discredited as science, represented an early attempt to link human consciousness with cosmic cycles. The Babylonians tracked planetary movements, the Egyptians aligned temples with solstices, and Islamic mathematicians charted star maps that preserved subtle harmonies. While modern astronomy rejects the predictive claims of astrology, it cannot deny the profound cultural intuition that human life reflects cosmic order. Synchronicity in this sense is an echo of a long-held belief that the brain and universe share hidden rhythms. Modern computational models push this further. When mapping the nodes of the cosmic web, galaxies connected by filaments of dark matter, scientists at the University of Bologna in 2020 compared the structure to simulations of neural networks. Remarkably, both systems showed similar distributions of connectivity, about 70% of mass and energy concentrated in filaments, with the remainder in isolated nodes. This structural synchronicity suggests that self-organizing systems, from neurons to galaxies, may follow universal principles of network formation. If the brain mirrors the cosmos in architecture, perhaps it mirrors it in dynamics as well, including the emergence of correlations that appear as coincidences in daily life. Yet science remains cautious. Skeptics argue that human perception is biased towards seeing order in randomness. The brain is a pattern recognition machine. It evolved to detect predators in foliage and to anticipate social cues. This survival function can lead us to overinterpret coincidences as meaningful. Still, even if the interpretation is biased, the phenomenon of synchronicity forces a deeper inquiry. Why should the universe produce a brain that interprets coincidence as meaning? Why should consciousness be structured to detect order even where none appears? Perhaps meaning itself is a property of the universe and the brain is tuned to uncover it. In cosmology, randomness and order coexist. The cosmic microwave background, radiation left from the Big Bang, shows tiny fluctuations that seeded galaxy formation. These fluctuations were random, yet from them emerged the structured universe. Similarly, genetic mutations are random, yet through natural selection they yield the order of complex life. At both cosmic and biological scales, randomness becomes the foundation of structure. Synchronicity may represent the psychological equivalent. Random events perceived as meaningful, guiding behavior and thought in ways that contribute to order within human experience. One of the most striking domains of synchronicity is creative discovery. Many scientists report breakthroughs arising not from calculation, but from coincidence. The chemist Auguste Kekulé envisioned the ring structure of benzene after dreaming of a snake biting its own tail. The discovery of penicillin by Alexander Fleming resulted from an accidental mold contaminating petri dishes. While these can be dismissed as accidents, their frequency in history raises questions. Is creativity simply chance filtered by persistence? Or do these coincidences reveal that the brain taps into deeper informational fields where solutions already exist? Some researchers exploring quantum cognition propose that thought may operate in superpositions, with ideas collapsing into insight under the right conditions, much like particles collapsing into definite states when observed. If so, the boundary between coincidence and causality begins to blur. The brain may not only passively receive information from the environment, but also participate in a larger network of informational exchange. In this sense, synchronicity is not anomaly, but evidence that consciousness is interwoven with universal patterns, and what appears random may be a shadow of hidden order. And yet the question remains unresolved. Does synchronicity point to a deeper connection between brain and universe, or is it simply an artifact of perception, a side effect of our pattern-hungry minds? Each new study, from EEG correlations with Schumann frequencies to cosmic network comparisons, deepens the mystery rather than resolves it. The evidence hints at a profound linkage but resists definitive proof. What makes this inquiry so compelling is not only its scientific implications but its existential ones. If synchronicity is real, then human consciousness may be far less isolated than we assume. It may be connected to planetary fields, to cosmic structures, to rhythms that bind galaxies and neurons alike. If it is illusion, then the illusion itself is telling that our brains are built to interpret the universe as meaningful, even when randomness reigns. But one question remains unanswered. If coincidences shape thought and thought shapes reality, then are we uncovering universal order or are we creating it? If coincidences hint at hidden connections, then the next step is to ask whether biology itself exploits the peculiarities of quantum mechanics. For decades, scientists assumed that quantum effects could not play a role in living organisms. The logic seemed straightforward. Quantum states are fragile, easily destroyed by heat and noise, and the warm, wet environment of cells appeared hostile to such delicate phenomena. Yet discoveries in the last 2 decades have forced a reconsideration. Quantum biology has emerged as a serious field of study, suggesting that life may not only tolerate quantum processes, but actively rely on them. Photosynthesis provides one of the clearest examples. In plants, light harvesting complexes capture photons from the sun and channel their energy toward reaction centers where chemical conversion begins. In 2007, experiments using ultra-fast laser spectroscopy revealed that the energy does not simply hop randomly between molecules. Instead, it appears to travel as a quantum wave, exploring multiple pathways simultaneously before collapsing into the most efficient route. This quantum coherence, lasting hundreds of femtoseconds, allows photosynthesis to achieve near-perfect efficiency. If plants can maintain quantum states to sustain life, it raises the question, could the human brain also harness similar effects to sustain thought? Another striking case is avian navigation. Migratory birds travel thousands of kilometers with remarkable accuracy, often across continents and oceans. Research indicates they may detect Earth's magnetic field using a protein called cryptochrome in their eyes. Evidence suggests that the mechanism involves quantum entanglement of electron spins, providing sensitivity to magnetic variations. Here, quantum physics directly informs behavior, linking subatomic processes with macroscopic action. The fact that evolution has harnessed entanglement for survival undermines the claim that quantum effects are irrelevant in biology. In humans, one of the most debated proposals is the orchestrated objective reduction model developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They suggest that microtubules, cylindrical structures inside neurons that support cell shape and transport, may serve as sites for quantum computation. According to the theory, quantum states within microtubules collapse in orchestrated patterns, generating moments of conscious experience. While controversial, this hypothesis attempts to bridge the gap between physics and awareness. Critics argue that maintaining quantum coherence in the brain's noisy environment is implausible, yet experimental hints of coherence in microtubules continue to attract attention. One study in 2014 reported that anesthetics, which suppress consciousness, appear to disrupt microtubule activity. This correlation suggests that microtubules may indeed be more than structural scaffolds. Other experiments have found oscillatory patterns within microtubules resonating at frequencies that could support coherent behavior. If confirmed, these findings would mean that the building blocks of neurons are not merely chemical processors, but quantum devices capable of information processing far beyond classical limits. The implications extend to memory and decision-making. Traditional neuroscience explains memory through synaptic plasticity, the strengthening or weakening of connections between neurons. But this model struggles to account for the persistence and integration of memory over decades. If microtubules or other quantum processes play a role, memory might involve states stored not only in synapses but in deeper informational fields, possibly linked to quantum entanglement. Decisions, too, may be less deterministic than once assumed, involving superpositions of potential outcomes that collapse into choice. This model could explain the unpredictability and creativity of human thought, which often defy purely mechanical description. Skeptics caution that quantum biology remains in its infancy. Evidence of coherence in photosynthesis and bird navigation is strong, but extending those findings to the human brain is speculative. The scale, complexity, and fragility of neural systems make definitive proof difficult. Nonetheless, research continues. Advances in quantum sensing technologies may one day allow direct measurement of quantum states in living neurons. If such states are found, they would revolutionize our understanding of consciousness, demonstrating that the mind is not only chemical and electrical, but quantum at its core. Even without definitive proof, the parallels are compelling. Just as photons travel multiple paths in plants before resolving into efficiency, thoughts often branch into possibilities before resolving into action. Just as birds navigate with entangled electrons, humans navigate decisions that sometimes feel guided by intuition beyond logic. Whether metaphorical or literal, these parallels encourage us to think of the brain as a quantum system embedded within a quantum universe. If the brain does use quantum mechanics, then it may also be subject to phenomena like non-locality. In principle, this would mean that consciousness could extend beyond the skull, influenced by correlations at a distance. Though no rigorous evidence yet supports telepathy or mind-to-mind communication, the framework of quantum entanglement keeps the question alive. Could collective consciousness emerge not from cultural sharing alone, but from genuine physical connections? Some experiments measuring correlations between human brainwaves and geomagnetic activity hint at such possibilities, though results remain contested. The broader implication is that consciousness may not be reducible to classical physics at all. If life exploits quantum mechanics, then the mind may be a quantum phenomenon inseparable from the universe's deepest structure. This would reframe the so-called hard problem of consciousness. Rather than asking how matter produces mind, we might ask how quantum information manifests as experience. The distinction between brain and universe would blur as both become participants in the same informational field. For philosophy, this shift recalls older traditions. Ancient thinkers in Greece, India, and the Middle East often spoke of the cosmos as alive, infused with a universal principle of order or mind. While modern science dismisses such views as metaphysical, quantum biology may reopen the door. The discovery that plants use coherence or that birds exploit entanglement suggests that life is fundamentally quantum. If so, ancient intuitions about unity between mind and cosmos may hold more truth than once acknowledged. Yet open questions remain. If microtubules orchestrate quantum states, why do they sometimes fail, as in neurological disease? Could conditions like Alzheimer's or schizophrenia reflect breakdowns not only of chemical pathways but of quantum coherence? And if the brain does process information quantum mechanically, does this explain why consciousness resists reduction to classical computation, making human thought different from even the most advanced artificial intelligence? As science probes deeper, the debate grows sharper. Some insist that classical neuroscience will eventually explain everything, while others argue that only by embracing quantum mechanics can we resolve the mystery of consciousness. Between these positions lies a frontier of uncertainty. Each new experiment, whether confirming or contradicting, pushes us closer to an answer, and so the question lingers at the edge of knowledge. If the brain harnesses quantum processes, does this mean consciousness is a local biological adaptation? Or does it mean we are participating in the same quantum fabric that governs stars, particles, and galaxies alike? If quantum biology hints that life itself may be entangled with deeper laws of physics, then the next step is to examine a principle at the very heart of quantum mechanics: the observer effect. In traditional physics, objects exist with well-defined properties independent of who measures them. A ball rolls down a hill whether or not anyone watches. But in the quantum world, experiments have shown something far stranger. Particles like electrons or photons appear to exist in multiple states at once, described by probabilities until they are measured. Measurement seems to collapse those probabilities into a single outcome. In other words, observation itself plays a role in shaping reality. The most famous demonstration of this is the double-slit experiment, first performed in the early 1800s with light and later repeated with electrons. It showed that particles passing through two slits interfere with themselves like waves, producing a striped pattern on a screen. Yet when detectors are placed to observe which slit the particle goes through, the interference disappears. The very act of observation forces the particle to behave like a particle rather than a wave. The conclusion unsettled generations of physicists. The line between observer and observed is not as clear as once believed. When applied to consciousness, the observer effect raises profound questions. What counts as an observer? Is it simply a measuring device, or does it require awareness? John von Neumann, one of the pioneers of quantum theory, argued that measurement could not be fully explained until the chain of observation reached consciousness. Eugene Wigner later proposed that consciousness might collapse the wave function itself, turning probabilities into reality. While many physicists today prefer interpretations that avoid placing mind at the center, the debate has never been fully resolved. Experiments continue to deepen the mystery. In 1999, researchers at the Weizmann Institute in Israel tested a variation of the double-slit experiment. They found that even weak measurement, gathering partial information about the particle's path, reduced the interference pattern. Observation did not have to be direct or conscious. Simply having the possibility of information existing was enough to alter the outcome. This suggests that information and reality are intertwined in ways physics still struggles to explain. If observation shapes outcomes at the quantum level, then what role might the human brain play? Each second, billions of photons strike the retina, each representing a quantum event. Neurons fire as ions cross channels, movements of particles governed by quantum rules. Conscious perception is built from countless such events. If consciousness participates in collapsing quantum states, then perception might be more than passive reception. It might be an active process that crystallizes reality out of probability. This possibility has led some researchers to explore whether consciousness and quantum measurement are two sides of the same phenomenon. Henry Stapp, a theoretical physicist, suggested that consciousness could be seen as the stream of choices among quantum possibilities. Each decision from firing a neuron to forming a thought could represent the collapse of a wave function. In this view, free will may not be an illusion, but a fundamental quantum process. Choices would not be determined solely by prior physical causes, but by probabilistic collapses influenced by awareness. Skeptics counter that no experiment has yet shown consciousness directly affecting quantum systems. They argue that measurement can be explained without invoking mind, that detectors and apparatus suffice. Still, the question persists because no consensus interpretation of quantum mechanics exists. The Copenhagen interpretation places collapse at measurement. The many worlds interpretation avoids collapse altogether by proposing branching universes, and newer models like decoherence describe interactions with the environment as sufficient. Yet none can fully explain why we experience one outcome rather than many. Consciousness remains the unresolved piece. Philosophically, this uncertainty invites speculation. If consciousness helps define reality, then the mind is not simply a byproduct of the brain. It is a participant in the unfolding of the universe. The subjective and the objective would not be separate but entangled. Perception would be creation, and thought would be woven into the structure of reality. This aligns with ancient perspectives that viewed the world as mind-like, where the act of knowing was inseparable from the world known. Scientific caution demands restraint. No evidence yet proves that human consciousness collapses wave functions, but experiments increasingly suggest that information and observation are fundamental to physical processes. And since the brain is the most advanced information processing system known, it remains a candidate for exploring these mysteries. New technologies, such as quantum computing and ultra-sensitive detectors, may one day reveal whether awareness has measurable effects on quantum outcomes. Consider the broader implications. If the brain's act of observation helps define reality, then each conscious moment participates in shaping the universe. Reality would not be a fixed stage on which life plays out, but a dynamic process in which observers are co-creators. The cosmos would not merely contain us, it would depend on us, at least in part, to actualize its possibilities. Such a view radically transforms our place in nature, from passive witnesses to active participants in the unfolding of existence. Even if consciousness does not collapse wave functions, the metaphor remains powerful. Our brains filter probabilities into certainties every day. From countless possible futures, we choose one path with every decision. Our perception turns chaotic sensory input into a coherent world. In this sense, whether or not we shape quantum outcomes, consciousness undeniably shapes experienced reality. The observer effect then may operate not only in physics but also in psychology. Awareness changes what is real for us. The open question persists. Are we discovering a deep law of the universe, or are we projecting human experience onto physics? The lack of closure may be the point. Science thrives at the boundary between known and unknown. The observer effect sits precisely there, hinting that the separation between brain and cosmos, between subject and object, may be thinner than we imagine. As experiments grow more refined, one outcome seems clear. Reality is not independent of information. Whether consciousness plays the decisive role or not, information lies at the foundation of physics. And since the brain is an engine of information processing, the overlap between mind and universe cannot be ignored. The mystery is not only how matter gives rise to mind, but how mind and matter define one another. But one question remains unanswered. If consciousness is bound up with observation, then is the universe aware only through us, or is it observing itself on every level through every interaction in ways we have yet to comprehend? If observation hints that consciousness and reality are intertwined, another frontier of research opens an even deeper mystery: the structural parallels between the brain and the universe itself. When astronomers map the cosmos on the largest scales, they find that galaxies are not scattered randomly, but woven into filaments and clusters, connected by invisible threads of dark matter and gas. This vast structure, called the cosmic web, stretches across billions of light years. Galaxies form nodes at the intersections of filaments, while immense voids span the spaces in between. The result is a universe that looks less like a uniform expanse and more like a living network. At first glance, this may seem purely astronomical. Yet when neuroscientists image the human brain, tracing the links between neurons, they find something eerily familiar. Neurons cluster into modules connected by axons that stretch across the cortex, with pathways forming hubs where information converges. When these brain networks are visualized, the patterns bear a striking resemblance to the cosmic web. In 2020, a team of researchers from the University of Bologna and the University of Verona directly compared the two systems. They analyzed the distribution of matter in the cosmic web and the connections between neurons in the brain. Despite the difference in scale, 27 orders of magnitude separate them, the two networks displayed similar statistical properties. Both balanced nodes and links in ways that maximized efficiency. Both demonstrated small world organization, where clusters are tightly connected locally, but also linked across long distances. In other words, the universe and the brain are wired in comparable ways. This discovery raises haunting questions. Is the similarity only coincidence, the inevitable result of networks governed by physics and mathematics? Or does it point to something deeper, a fractal-like pattern that repeats across nature, from the microscopic to the cosmic? Consider the numbers. The observable universe contains about 100 billion galaxies. The human brain contains about 86 billion neurons. Both numbers fall within the same order of magnitude. While the content differs, stars and galaxies versus neurons and synapses, the scale echoes as though nature were mirroring itself. The brain seems to be a universe within, and the universe a brain without. Philosophers have long speculated about such correspondences. The ancient Hermetic maxim declared, "As above, so below," suggesting that patterns repeat across levels of existence. Modern science usually avoids such mystical parallels, yet the mathematics of networks shows that similar constraints may produce similar shapes, whether in a brain or in the cosmos. Information, after all, must flow efficiently through both systems. Energy must be distributed without waste. Form follows function, whether neurons transmit signals or galaxies channel matter. Still, the resemblance is not merely visual. Some researchers propose that the universe itself may process information like a brain. Astrophysicist Franco Vazza and neurosurgeon Alberto Faletti suggested that cosmic evolution resembles neural activity, with matter and energy moving along pathways comparable to electrical impulses. In this analogy, the universe could be seen as a kind of giant neural network, evolving patterns of complexity across billions of years. Such ideas border on the speculative, but they stir the imagination. If the universe shares structural features with the brain, could it also share something of its function? Could the cosmos itself be capable of awareness, or at least of information processing on a scale beyond comprehension? If so, human consciousness might not be an isolated anomaly, but a local expression of a universal property. Critics warn against stretching the metaphor too far. Galaxies do not think, and cosmic filaments do not fire like neurons, yet the parallels persist, inviting reflection. Even if the resemblance is structural rather than functional, it suggests that the same mathematical rules guide both neural and cosmic architectures. Order emerges from chaos in similar ways, no matter the scale. Perhaps what we call consciousness arises wherever complexity reaches a threshold. If so, the brain is one place where the universe wakes up to itself. In this view, every conscious mind is a mirror held up to the cosmos, reflecting its vast design and miniature. Our thoughts would not be separate from the universe, but continuations of the same pattern. The comparison also changes how we see ourselves. If the brain is a microcosm of the universe, then self-knowledge and cosmic knowledge are two aspects of the same quest. To study the brain is to glimpse the architecture of the cosmos. To map galaxies is to trace patterns that echo in our own minds. The division between inner and outer worlds begins to dissolve. This mystery pushes us toward a final question. Is the similarity between brain and cosmos merely a mathematical accident, or is it a clue to a deeper truth that consciousness and universe are bound by the same underlying code? If the large-scale architecture of the cosmos mirrors the neural networks of the brain, the question deepens when we consider how information might move through such structures. At the smallest scales of physics, quantum mechanics reveals a form of connection unlike anything in classical science: entanglement. Entanglement is a phenomenon in which two or more particles become correlated in such a way that their states cannot be described independently. Change one and the other responds instantly, no matter the distance between them. This was not speculation, but experimentally demonstrated. In 2015, scientists at Delft University in the Netherlands closed a major loophole in entanglement experiments, showing that the effect could not be explained away by hidden signals. In 2017, another team pushed the distance further, entangling photons between ground stations and a satellite in orbit more than 1,200 kilometers above Earth. The results confirmed that entanglement functions as if information passes outside space and time. For decades, physicists like Albert Einstein resisted the idea, calling it spooky action at a distance. Yet entanglement has moved from paradox to practical tool. Quantum computers now exploit it to perform operations far beyond classical limits. Quantum communication systems use it to achieve secure data transfer, as any interference would instantly disturb the entangled state. The phenomenon is real, measurable, and increasingly central to emerging technology. This brings us back to consciousness. The human brain operates in a warm, noisy environment where quantum effects are usually thought to collapse quickly. Traditional neuroscience assumes that thought is the product of electrochemical signals alone, unaffected by quantum strangeness, but new research challenges this assumption. Studies of photosynthesis show that plants use quantum coherence to transfer energy with extraordinary efficiency. Birds may navigate using entangled particles in their eyes, detecting Earth's magnetic field. If biological systems can exploit quantum phenomena, then the possibility that the brain does so cannot be dismissed outright. One controversial proposal, known as the ORC-OR theory, suggests that microtubules inside neurons support quantum states that could influence consciousness. While debated, the idea forces a reevaluation of whether awareness is purely classical or partly quantum. If microtubules or other subcellular structures maintain quantum coherence, then entanglement could, in principle, extend consciousness beyond the skull. This speculation gains traction when compared with subjective reports of synchronicity, intuition, or sudden insights that seem to bypass normal information channels. While such experiences are difficult to study scientifically, they raise the question of whether entanglement might provide hidden pathways for information transfer. Could two brains, under certain conditions, share correlations in the same way particles do? Controlled experiments in parapsychology have long searched for evidence of telepathy, usually with inconclusive or disputed results. Yet if entanglement is real and universal, then the theoretical framework exists for such links, even if the effect is subtle and hard to detect. The broader implication is that consciousness itself might be non-local. Rather than confined to the skull, awareness could be distributed through networks of entangled particles, linking individuals across distances. In this model, thoughts are not only internal processes, but also interactions with a shared quantum field. This would not mean mind reading in the traditional sense, but a deeper form of connectedness, where consciousness is inherently woven into the universe's fabric. Skeptics argue that entanglement does not transmit usable information in the way signals do. Quantum mechanics forbids faster-than-light communication, yet the correlations exist, undeniable and persistent. Even if entanglement cannot be harnessed as a direct channel of thought, it may still underpin the unity of consciousness, the sense that the self is not a collection of independent parts, but a coherent whole. Just as entangled particles cannot be separated conceptually, perhaps consciousness cannot be reduced to isolated neural firings. The analogy extends further. If galaxies in the cosmic web are nodes of matter and neurons in the brain are nodes of information, then entanglement might serve as the invisible threads binding them. Local processes generate complexity, but hidden correlations ensure coherence. The universe, like the brain, may function as a unified system precisely because of these unseen connections. This perspective redefines individuality. If consciousness has quantum roots, then the boundaries between minds may be more porous than assumed. Each person would still experience a private stream of awareness, yet beneath that surface, all streams might emerge from the same quantum ocean. What appears separate at the classical level could be deeply connected at the quantum level. Practical evidence remains scarce. Brain imaging does not yet reveal entanglement. No laboratory has proven non-local consciousness effects beyond doubt. Still, the history of science is full of phenomena that seemed impossible until the right tools emerged. Electricity, once mysterious, is now routine. Magnetism, once magical, is now measured. Entanglement, once paradoxical, is now engineered into devices. Consciousness may follow the same path, from speculation to measurable quantum phenomenon. For now, the parallels raise more questions than answers. Why does the universe allow entanglement? Why does it persist across vast distances without decay? Could this same property underlie the coherence of thought? If so, then consciousness is not merely produced by the brain, but linked to the universe in ways that defy classical boundaries. As one possibility fades, another emerges. If entanglement hints at non-local awareness, then how does this relate to time itself, the very stage on which both physics and thought unfold? If entanglement challenges our understanding of space, then time presents an equally profound puzzle. Physics and consciousness both confront the mystery of temporal flow, yet they approach it from opposite directions. Physics describes time as a dimension woven into space-time, measurable and relative. Consciousness experiences time as a sequence, a steady unfolding of moments. The two perspectives do not align easily. Clocks measure time with remarkable precision. The most advanced atomic clocks, using oscillations of strontium atoms, drift less than 1 second over the age of the universe. They define seconds by counting cycles of electromagnetic radiation, each tick as steady as the next. Yet human perception tells a different story. Minutes in danger or excitement stretch into what feels like hours. Hours of routine collapse into fleeting impressions. The discrepancy suggests that time as experienced by the brain is not a direct reflection of physical time. Neuroscience explains part of this divergence. The brain constructs temporal experience by synchronizing neural oscillations, from slow delta waves to fast gamma waves. These rhythms coordinate perception, memory, and anticipation. When attention intensifies, neural circuits fire faster, packing more events into each perceived interval, making time seem longer. When the mind drifts, fewer events register, compressing time. Experiments show that dopamine, a key neurotransmitter, alters time perception, making intervals appear shorter or longer depending on its levels. But even with these explanations, anomalies remain. For example, near-death experiences often include a sense of timelessness, where entire lifetimes appear reviewed in seconds. Psychedelic substances can distort time so drastically that minutes feel infinite. Such phenomena imply that temporal perception is highly elastic, shaped not only by neural rhythms, but possibly by deeper processes. Physics complicates the picture further. Einstein's theory of relativity shows that time is not absolute. Moving at high speeds or near strong gravitational fields causes time dilation, where clocks tick at different rates depending on their conditions. This has been tested with aircraft, satellites, and even GPS systems, which must correct for relativistic effects to maintain accuracy. If time is relative, then the brain's flexible perception may not be so alien after all. It may echo the relativity built into the universe. Speculation arises when the two domains intersect. If the brain's rhythms are influenced by quantum processes, then time perception could involve coherence at scales deeper than classical neurobiology. Quantum systems do not move step by step but evolve as superpositions until observation collapses them. Could consciousness, operating partly in this domain, experience time not as a strict sequence, but as a probability landscape? Some interpretations of quantum theory even suggest that past, present, and future coexist, and that what we call the flow of time is a product of observation. If so, then subjective time may reveal something fundamental. The brain, through consciousness, could be sampling a deeper structure of reality, where time is not linear but emergent. Each moment of awareness would not simply follow the last, but crystallize from a field of possibilities. This could explain why altered states of consciousness bend time so dramatically. The brain's normal filtering loosens, allowing glimpses of a nonlinear temporal order. Memory and anticipation provide further evidence. Unlike clocks, the brain is never in the present alone. It constantly compares the now with stored experiences and predicts the next instant. This binding of past, present, and future into one continuous narrative might be the essence of temporal awareness. Physicists note that the arrow of time, the direction from past to future, is tied to entropy, the tendency of systems to move from order to disorder. Consciousness, however, seems to impose its own arrow, constructing meaning and continuity from otherwise chaotic inputs. The comparison raises unsettling questions. If time is relative and entanglement transcends distance, could consciousness also transcend temporal boundaries? Reports of precognition or déjà vu, while scientifically controversial, suggest experiences where information seems to leak from future to present. While no controlled experiment has confirmed such phenomena, their persistence in human experience invites inquiry. If entanglement links particles across space, might similar principles link moments across time? Some physicists propose that the universe is a block of space-time where past, present, and future all coexist. In this model, time does not flow, it simply is. Consciousness would then move through this block, creating the illusion of passage. If this view is correct, then the brain is less a timekeeper and more a navigator, selecting slices of space-time to assemble into a coherent experience. This would explain why physical time remains consistent while psychological time stretches and contracts. It is a process of navigation, not measurement. Other models go further, suggesting that time itself is emergent, arising from entanglement and information flow. In this view, time is not a fundamental property of the universe, but a byproduct of deeper correlations. Consciousness, then, might be both shaped by and shaping time, participating in the same processes that generate temporal order. The distinction between inner and outer time would blur, pointing again to a possible unity between brain and cosmos. The implications are vast. If consciousness is tied to the emergence of time, then studying the brain could reveal not just how humans perceive moments, but how the universe generates them. Time would no longer be a neutral backdrop, but a dynamic aspect of reality co-created by observation and information. In this framework, the elasticity of psychological time is not an error, but a window into the flexibility of time itself. Yet this evidence raises new scientific questions. If the brain experiences time differently from physical clocks, does this indicate a deeper connection to the universe's structure? Or is it merely a limitation of neural processing? And if time is not fundamental, then what does it mean for consciousness, which depends so deeply on sequence and continuity? If consciousness bends time into elastic sequences of past, present, and future, then memory becomes the anchor that allows this continuity to exist. Without memory, time would collapse into isolated instants. Yet what exactly is memory, and where does it truly reside? Neuroscience has traditionally located memory in synaptic connections. When neurons fire together, the synapses between them strengthen, forming patterns that encode experience. This model, first outlined by Donald Hebb in 1949, remains the foundation of modern cognitive science. Experiments confirm that disrupting synaptic pathways with drugs or injury impairs memory, while practice and repetition strengthen it. Memory, in this view, is chemical and structural, etched into the brain's wiring, but this explanation faces limits. Human memory can recall faces from decades earlier with astonishing clarity. It can store languages, skills, and images in volumes far exceeding what any physical storage medium of comparable size could achieve. Some researchers estimate the brain's capacity at around 2.5 petabytes, roughly the equivalent of 3 million hours of television. Yet, unlike digital storage, the brain is dynamic. Memories are not fixed files, but reconstructed, with each recall vulnerable to distortion yet remarkably persistent. This persistence raises questions. If synaptic turnover occurs regularly, neurons die, proteins degrade, and synapses remodel, how can memories survive for decades? Some theories suggest that memory is stored not only in synaptic weights but also in molecular structures, perhaps even within the cytoskeleton of neurons. Others propose that DNA methylation and epigenetic markers preserve traces of experience across time. Still, the sheer stability of memory in a constantly changing biological system hints that more may be at play. Here, speculation enters. Could memory extend beyond the brain's physical substrate? One hypothesis suggests that memory may be a field phenomenon distributed through patterns of electromagnetic or quantum coherence. British biologist Rupert Sheldrake proposed the controversial idea of morphic fields, suggesting that memory is not solely stored in the brain, but exists in resonance with fields of information shared across organisms. Though criticized for lack of empirical proof, the concept touches on a question mainstream science has yet to fully resolve. Is memory entirely local or partly non-local? Physics provides analogies. In quantum mechanics, information is never destroyed. Even when particles fall into a black hole, theoretical models suggest their information persists, encoded on the event horizon. This principle, that information is conserved, raises the possibility that memory too may have persistence beyond the physical brain. If the universe itself safeguards information, could consciousness tap into this reservoir? Experimental evidence is scarce but intriguing. Some studies of near-death experiences report vivid life reviews where entire lifetimes seem recalled in seconds. Others document cases of sudden, detailed memory emerging after brain injury, as if previously inaccessible information became available. While not definitive, these anomalies suggest that memory may not be confined to synaptic chemistry alone. Technology also challenges assumptions. Artificial intelligence systems trained on massive datasets exhibit emergent memories that are not stored in single locations but distributed across networks. Similarly, holography demonstrates how information can be stored non-locally. Each part of a hologram contains the whole image in lower resolution, Some theorists suggest the brain functions holographically, with memory distributed throughout neural fields rather than localized in specific spots. This would explain why partial brain damage often reduces but does not erase memory, much as a torn hologram still reveals the entire picture. The concept of non-local memory intersects with the universe itself. If the brain resembles the cosmic web in structure, and if information is fundamental to reality, then memory could be an interaction with larger informational fields. This would not mean that personal memories float in space awaiting retrieval, but that the act of remembering involves resonance with universal information structures. Just as a radio tunes into frequencies, the brain might align with patterns embedded in a deeper informational layer of reality. Skeptics argue that such ideas overreach. No experiment has conclusively shown memory existing outside the brain, yet even within accepted neuroscience, mysteries remain. Why can certain memories be recalled instantly while others vanish without trace? Why do smells evoke memories more powerfully than images or sounds? Why do traumatic events burn into the mind with such resilience? These questions hint at processes beyond simple synaptic change, pointing to mechanisms we do not yet fully grasp. If memory is partly field-based, the implications extend to collective memory. Cultures, myths, and traditions preserve patterns across generations, functioning almost like a distributed memory system for humanity. Carl Jung's concept of the collective unconscious resonates with this idea, proposing archetypes shared across individuals. Whether rooted in biology, culture, or fields beyond the brain, memory shapes not only personal identity, but the continuity of civilization itself. The deepest implication is existential. If memory is not fully local, then it may not be extinguished when the brain ceases. The physical substrate decays, but the informational patterns may persist, just as data encoded in waves can outlast the medium that generated them. This possibility fuels debates about reincarnation, ancestral memory, and the persistence of consciousness. Though controversial, it reflects a consistent theme. Memory, like time, may not be confined to the linear material framework we assume. As one question resolves, another arises. If memory truly interacts with broader fields, then what role might the unseen majority of the universe, dark matter and dark energy, play in storing or transmitting such information? Could the invisible scaffolding of the cosmos hold not only galaxies together, but also the echoes of experience itself? If memory raises the possibility of hidden fields, then the next mystery emerges from the very structure of the cosmos itself. Modern astrophysics has revealed that the matter we see, stars, planets, gas, and dust, accounts for less than 5% of the universe. The rest consists of dark matter and dark energy, invisible substances that shape cosmic evolution but remain undetected by direct instruments. This imbalance invites a question: could these unknown components play a role in consciousness? Dark matter was first proposed in the 1930s by Fritz Zwicky, who observed that galaxies in clusters moved too fast to be held together by visible mass alone. Later, Vera Rubin confirmed similar anomalies in galactic rotation curves, showing that stars at the edges of galaxies orbit as if pulled by unseen mass. Today, dark matter is estimated to make up about 27% of the universe, while dark energy, driving cosmic expansion, accounts for nearly 70%. Despite decades of study, their exact nature remains a mystery. Physicists search for dark matter through underground detectors, particle colliders, and astronomical surveys. Candidates include weakly interacting massive particles, axions, or sterile neutrinos, but no direct detection has yet succeeded. The invisible dominates, yet it evades measurement. Consciousness, in its own way, presents a parallel puzzle. It shapes experience and action, yet it eludes reduction to purely material processes. Both dark matter and consciousness occupy central roles while remaining unresolved. Some theorists suggest that consciousness could interact with dark matter fields. The idea is speculative, but the logic stems from scale. If the brain and universe share structural parallels, and if most of the universe is dark, then perhaps brain function resonates not only with visible matter, but also with hidden components. Just as dark matter holds galaxies together, could it also serve as a medium for the coherence of thought? To consider this, we examine the brain's energy use. The brain consumes about 20% of the body's energy despite representing only 2% of its mass. This efficiency suggests finely tuned processes. If quantum effects enhance its function, as some theories propose, then subtle interactions with dark matter fields cannot be ruled out. After all, dark matter interacts gravitationally with ordinary matter. It permeates every region of space, including the very volume occupied by the brain. In that sense, consciousness already coexists with dark matter, whether or not it perceives it. Dark energy complicates the picture further. Discovered in 1998 through observations of distant supernovae, dark energy accelerates the universe's expansion, counteracting gravity. If this energy represents a property of the vacuum itself, then consciousness, grounded in quantum fields, may operate within the same framework. Some physicists speculate that vacuum energy fluctuations play roles in quantum processes. If so, then the brain's most fundamental operations could be influenced by the same hidden forces that drive cosmic acceleration. Critics caution against overreaching. Dark matter has not been shown to interact with anything beyond gravity, and consciousness has no measurable link to cosmic expansion. Yet the analogy remains compelling. Both represent gaps in knowledge, central mysteries bridging the seen and unseen. To study one is to confront the limits of science. To imagine a connection is to recognize how incomplete our understanding remains. Experiments may someday clarify the relationship. If dark matter particles can be identified, researchers could test whether they influence biological systems. Already, some experiments search for annual modulation in detectors caused by Earth's orbit through dark matter fields. If living systems showed similar patterns, it would suggest a subtle connection. None have yet been found, but the possibility illustrates how questions of physics and consciousness can converge. Another approach considers information. Some cosmologists propose that dark matter and dark energy may not be substances, but emergent phenomena, reflecting how information organizes in space-time. If reality at its core is informational, then both cosmic structure and consciousness emerge from the same substrate. In this view, dark matter is not separate from awareness, but another expression of the universe's informational code. Consciousness and cosmos would be parallel outputs of the same system. Even without direct evidence, the thought reshapes perspective. We often imagine ourselves as isolated beings, observing a vast, indifferent universe. But if unseen matter and energy permeate not only galaxies but our own bodies, then we are literally immersed in the unknown. Consciousness might not only arise within this environment, but also interact with it in ways we cannot yet measure. The implications are profound. If dark matter stabilizes galaxies, perhaps it also stabilizes the coherence of thought. If dark energy drives expansion, perhaps it also influences the forward momentum of time as experienced by the mind. These ideas remain speculative, yet they underscore a truth. The greatest mysteries of the cosmos and of consciousness both lie hidden, shaping reality from behind a veil. As one possibility fades, another emerges. If the mind may be immersed in hidden fields of dark matter and energy, then what of the structures within the brain itself, specifically the microscopic components that some believe may operate at the quantum level? Could the key to linking consciousness and the universe be found not only in the stars, but in the architecture of neurons themselves? If dark matter and dark energy represent the hidden framework of the cosmos, then perhaps the equivalent mysteries within the brain are found not in its overall structure, but in the microscopic scaffolding of its cells. For decades, neuroscientists assumed neurons communicated only through electrical impulses and chemical signals. Yet, a controversial hypothesis suggests that deeper processes may unfold inside the very architecture of neurons, processes that may connect consciousness to the quantum realm itself. At the center of this debate lie microtubules. These are tiny cylindrical polymers composed of proteins called tubulins that form part of the cytoskeleton, the structural framework that supports the shape and transport functions of cells. In neurons, microtubules organize the pathways by which materials are moved along axons and dendrites. They are essential to life, but some researchers believe they may also serve as more than structural supports. They may act as quantum processors inside the brain. In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed the ORC-OR theory, orchestrated objective reduction. According to this model, microtubules inside neurons are capable of sustaining quantum states, much like particles in quantum computers. These quantum states collapse in orchestrated patterns, giving rise to moments of conscious awareness. Instead of neurons simply firing electrical signals, consciousness would emerge from the quantum computation unfolding inside microtubules. The idea was bold, uniting physics, neuroscience, and philosophy. Yet it was also met with heavy criticism. Skeptics argued that the warm, wet, and noisy environment of the brain was hostile to delicate quantum states, which typically collapse quickly under external influence. Maintaining coherence in biological tissue, they claimed, was virtually impossible. For decades, this critique seemed decisive, but in recent years, evidence has emerged that quantum phenomena can indeed persist in living systems. Photosynthesis in plants, navigation in migratory birds, and even the olfactory process of smell all appear to exploit quantum coherence. These discoveries reopen the possibility that the brain, too, might harness quantum effects. If plants can direct energy with near-perfect efficiency through quantum resonance, why couldn't microtubules in neurons support similar processes? Microtubules display remarkable properties. They are highly ordered, with repeating protein lattices that resemble computational networks. Their structures exhibit resonant vibrations in the megahertz to gigahertz range, frequencies that could, in theory, interact with quantum fields. Some experiments suggest that microtubules may even shield delicate states from environmental noise, though results remain inconclusive. If true, ORC-OR would suggest that consciousness is not simply a byproduct of complex neural connections, but a fundamental process tied to the quantum structure of reality itself. Each conscious moment would represent the collapse of quantum states in microtubules, linked directly to the geometry of space-time. Awareness, in this sense, would not only arise from the brain, but would participate in the unfolding of the universe. Critics still argue against the model, noting that no definitive experimental proof exists. Yet the mystery persists. Conventional neuroscience explains much about perception and behavior, but it struggles to account for subjective experience. The raw feeling of awareness, often called the hard problem of consciousness. Quantum theories, though speculative, attempt to bridge this gap by connecting mind to fundamental physics. Even if ORC-OR is incorrect in its details, the search itself reveals a deeper truth. Consciousness may not be fully explainable by classical biology alone. Whether through microtubules or other mechanisms, the possibility of quantum involvement forces us to rethink the boundaries of mind and matter. It suggests that the brain is not only a biological organ, but also a gateway into the underlying fabric of reality. The implications ripple outward. If microtubules truly engage with quantum processes, then consciousness may not be confined to individual brains. Quantum states can entangle across distance, linking particles instantly no matter how far apart. Could human awareness mediated by quantum coherence in microtubules also entangle with other systems, or even with the cosmos itself? If so, then consciousness might not be a private phenomenon but a universal one, woven into the very structure of space-time. Experiments continue to probe these questions. Studies investigate whether anesthetics, which are known to disrupt consciousness, act by interfering with quantum processes in microtubules. Others examine whether microtubule vibrations correlate with patterns of brain activity measured by EEG. Each result adds a fragment to a larger puzzle, though the complete picture remains elusive. The mystery of microtubules, like the mysteries of dark matter and cosmic structure, challenges us to look beyond what is visible. The ordinary explanations, neurons firing, galaxies spinning, cannot fully capture the depth of what is observed. Something hidden, whether in the stars or within cells, continues to shape reality in ways we do not yet understand. And so, the question lingers. Are microtubules merely biological scaffolds, or are they the quantum keys to consciousness, linking the human mind with the architecture of the universe? The brain, often described as the most complex object we know of in the observable universe. It weighs about 1.4 kilograms, makes up only about 2% of the human body's mass, and yet it consumes roughly 20% of the body's total energy. On average, this amounts to about 20 watts, comparable to the light from a small household bulb. The numbers seem modest, but what emerges from this continuous consumption is astonishing. Perception, language, memory, reasoning, and self-awareness. The puzzle is not just how the brain uses this energy, but whether its efficiency points to processes that classical physics alone cannot explain. Every neuron communicates through electrical impulses known as action potentials. When a signal fires, ions cross the cell membrane, producing voltage changes. Multiply this process by 86 billion neurons, each forming thousands of synaptic connections, and the result is a vast web of activity consuming glucose and oxygen at a steady rate. Functional MRI scans reveal how energy use spikes in specific regions when tasks are performed, such as visual processing or problem solving. Yet overall, the brain's consumption rarely rises far above baseline. A student solving equations or a pianist performing a concerto does not burn dramatically more fuel than someone sitting quietly. This consistency hints at an underlying optimization beyond ordinary computation. Modern computers, by contrast, devour energy when tasked with complex calculations. A supercomputer like Fugaku in Japan or Frontier in the United States consumes tens of megawatts, enough to power thousands of homes, to perform operations that the brain accomplishes seamlessly and quietly. The disparity suggests that biological computation operates on principles different from classical digital systems. Is it simply the parallel architecture of neurons, or could quantum effects amplify efficiency in ways not yet recognized? Theories like ORC-OR imply that microtubules within neurons could sustain quantum processes, making use of energy more effectively than expected under classical models. If quantum coherence allows multiple states to be processed simultaneously, the brain might achieve complex tasks while expending minimal power. This possibility aligns with evidence from nature, where systems like photosynthesis achieve near-perfect efficiency by exploiting quantum resonance. Just as plants funnel energy with extraordinary precision, neurons may harness hidden mechanisms to maximize the impact of every joule. But the story deepens when we consider how the brain manages and regulates energy. Neurons are not uniform. Some regions consume far more than others. The cerebral cortex, responsible for higher cognition, uses disproportionate energy compared with simpler brain structures. Glucose uptake in cortical areas can be measured using positron emission tomography, revealing hotspots of activity. Yet even here the balance is delicate. Deprivation of oxygen or glucose for just minutes can cause irreversible damage, underscoring how tightly life and consciousness are tied to energy flow. This raises a profound question. Is consciousness itself an emergent property of energy dynamics? If energy underpins every process, then awareness might represent a highly ordered pattern of energy use, one sensitive to quantum-level interactions. In this view, the brain is not merely a consumer of fuel, but a regulator of flows that align with universal laws. Thermodynamics tells us that energy can neither be created nor destroyed, only transformed. When neurons fire, chemical potential is converted into electrical activity, then dissipated as heat. But the informational structure, the pattern of how these transformations unfold, may hold the key to consciousness. Consider entropy, the measure of disorder. Living systems maintain low entropy states by exporting disorder into their environment. The brain, in particular, operates at the edge of order and chaos, sustaining patterns of activity that balance stability with flexibility. Electroencephalography reveals oscillations in distinct frequency bands, from slow delta waves during deep sleep to rapid gamma waves linked to attention. These rhythmic patterns represent coordinated energy states across millions of neurons. Some scientists propose that consciousness emerges when these oscillations achieve synchrony, binding distributed processes into unified awareness. The efficiency of this synchronization may depend on energy being used in precise, almost quantum-like ways. The comparison to artificial intelligence is instructive. Modern AI models trained on vast datasets require enormous computational resources. Training a large neural network can consume as much energy as the lifetime output of several cars. Yet the human brain, operating on 20 watts, surpasses AI in adaptability, creativity, and context awareness. If energy is the currency of thought, the brain spends it with remarkable thrift. Could it be that nature has discovered mechanisms, perhaps quantum enhanced, that we are only beginning to glimpse? Experiments are exploring this frontier. Studies of brain metabolism under anesthesia show that loss of consciousness corresponds with disruption of coherent energy patterns, even when overall consumption remains high. This suggests that it is not the amount of energy alone, but the organization of its use that determines awareness. Similarly, research into meditation and altered states of consciousness indicates shifts in brain oscillations without dramatic changes in energy intake, reinforcing the idea that pattern, not volume, matters most. The brain's energy story also connects to the cosmos. Stars burn nuclear fuel, galaxies rotate with hidden mass, and the universe expands under the influence of dark energy. At every scale, energy organizes structure. The brain, on its tiny stage, mirrors this principle, turning steady flows of fuel into emergent complexity. Could consciousness then be seen as one more manifestation of the universal rule, that energy, when organized at the right scale, produces new levels of order? If so, the brain may not be unique, but one node in a continuum of energy-driven systems, from atoms to galaxies. Skeptics might argue that energy use can be explained without invoking quantum processes, that classical biophysics suffices, and yet each new discovery in quantum biology challenges that boundary. If coherence guides photosynthesis, if entanglement aids bird navigation, why not extend the possibility to neural computation? The efficiency gap between the brain and machines remains a fact demanding explanation. Whether the answer lies in undiscovered classical mechanisms or in quantum phenomena remains unresolved, but the question itself deepens the mystery. When a thought arises, it does not weigh more, nor does it consume dramatically more glucose than silence. Yet it changes everything about experience. The same 20 watts that could light a bulb can produce awareness of self and universe. This proportionality feels almost paradoxical. Could it be that energy, channeled through ordered patterns at multiple scales, gives rise to a property we call consciousness? Or does energy serve only as the substrate, while the true explanation lies in the quantum informational structure beneath? As we consider these possibilities, one observation remains clear. The brain's energy use is both astonishingly efficient and deeply mysterious. It challenges our definitions of computation, information, and even life itself. And it raises the next question: if energy sustains consciousness within the brain, could similar principles operate at larger scales, hinting that the universe itself might harbor forms of awareness beyond our own?